Welcome to the 2023 NASA STEM Enhancement in Earth and Space Science High School Intern Science Symposium. SEAS is a collaboration between NASA and the University of Texas at Austin's Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and been hired by NASA working on missions such as Europa. In 2023, we received almost 2,000 completed applications, and we selected 200 students in 10th and 11th grades as participants who is assigned to 18 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their project. Interns heard from 10 different NASA subject matter experts during the SEAS speaker series and highlighted NASA missions, opportunities, and careers during the course of this internship. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, the managers of this program, welcome to NASA SEAS 2023. Today, we will welcome 14 teams and individual project video presentations. We will divide the afternoon into 2 sessions with one 20-minute break at 2:30 Central Time. Project video presentations will either be 5, 10, or 20 minutes in length, followed by Q&A. Please post your questions on the slido.com website and use code SEAS23. Here is our schedule for the day. We will have presentations by teams followed by 5 or 10-minute Q&A. We will invite each team presenting to turn on their cameras and their mics to answer the questions posed by those that are listening. During the 20-minute break, we invite you to watch the video highlights of the student intern produced products as part of the Earth and Space Science and Python projects. Our first presentations are by interns in the Eclipse Payload project group. Next slide. Students conducted intensive research into high altitude ballooning with an emphasis in monitoring atmospheric conditions. During this project, students developed a small engineering payload that will be deployed on high altitude balloons on April the 8th, 2024 for the total eclipse. Working with their mentors, the team developed the payload along with supporting electronics and systems required to conduct a test with a given sensor. A special thanks to mentor Adam Noakes and Melissa Poore for their guidance and expertise. Please welcome the Eclipse Payload project team presenting their high altitude Eclipse ballooning project.
Hi, everybody. Welcome to the NASA SEAS 2023 High Altitude Eclipse Payload Team presentation. We're so thankful to have you guys here to listen to our project and to what we have done with our research.
Hello, I'm Alexander Beckman, and I'm from Indianapolis, Indiana.
Hi, my name is Ella Brochu, and I'm from Mobile, Alabama.
I'm Brian De Jesus, and I'm from Bronx, New York.
Hey, I'm Jorge Hernandez, and I'm from Bronzeville, Texas.
Hi, everybody. My name is Nick Mendez, and I'm from Caldwell, Idaho.
Hi, my name is Anna Reveles Leon, and I'm from Richmond, Virginia.
My name is Ryan Schaefer, and I am from Philadelphia, Pennsylvania.
And I'm Raj Sinha. I'm from Houston, Texas, and I'd like to extend a thank you to Professor Adam Noakes and Melissa Poore for their guidance and help during this project.
For the NASA SEAS intern project, we were given the NEBP. NEBP is the Nationwide Eclipse Ballooning Project. This project included high altitude ballooning, which recorded atmospheric data. In terms of high altitude ballooning, there's been a huge increase in studies. As you see on the graph on the right, we see how Eclipse ballooning studies has increased from 1850 to 2000s. A study from the Royal Society of Publishing Records has also shown how temperature is affected by solar eclipse.
Another form of data was from the National Library of Medicine, who recorded increased wind speeds in 2009 eclipse in South Korea. And while there has obviously been lots of data collected during eclipses, high altitude ballooning data is actually quite rare. In the last eclipse in 2017, they collected high altitude ballooning data in Carbondale, Illinois. However, this was very minimal, and in the 2023 and 2024 eclipses, we'll be trying to collect far more data about the upper atmosphere.
Obviously, with these experiments and research, it is highly important to ask ourselves, why are we doing this and the significance? Obviously, we've already talked about this, but it's highly important to understand how our stratosphere and our atmosphere reacts to different variables, this being solar and annual eclipses. We need to learn more about Earth's atmosphere and how it can change depending on climate change or any other experiences. It is also highly important to expand knowledge on researching and on the atmosphere, as well as give opportunities to lower income communities so they can also create similar research projects like this one.
We did have to do prior research before starting this project. The NASA SEAS program gave us different modules so that we could learn about climate change, space exploration, and NASA technology. We also got more specialized modules that talked a lot more about wiring, forming the balloon, and actually launching the balloon.
So for our mission objectives, our first mission objective was to create a functional balloon for the annual and total solar eclipses. We were going to record temperature, humidity, pressure, and camera data. Our second objective was to perform a tethered launch before the eclipse. Our third was to analyze atmospheric data for a better understanding of the eclipse's effect on the atmosphere. And the fourth was to complete a research paper on the atmospheric effects of eclipses.
Here we have a Gantt chart that kept us on track and organized about our tasks and what days they needed to be completed.
Project. Before we began assembling, we divided into groups of 2. These groups resulted in Raspberry Pi and Arduino.
So we had to settle on, we were given a Raspberry Pi and Arduino. We had to pick which one we wanted to use. We ended up going with the Raspberry Pi because all of our sensors were compatible with both, but our camera was only compatible with the Raspberry Pi, and pin mappings were also a lot easier to find on the Raspberry Pi.
The next thing we had to consider were sensors. And with this, there are a lot of constraints that we have to keep in mind to ensure that we're receiving accurate data, like extreme atmospheric conditions such as temperature and low pressure.
So we settled on the BME 280 because it's lightweight, accurate, versatile, and it measures all our atmospheric conditions like temperature, humidity, and pressure. And based on pressure, we calculate the altitude that our balloon is flying at.
Because we'll be flying during an eclipse, we'd like to receive visual data. And to do this, we had a couple options like the ArduCam Module 3, PiCam Module 2 and 3, and infrared cameras to choose from.
And all of these different cameras had very specific coding, which we were able to achieve, like an initial start and a possible reboot, as well as a code for automatic lens fixation.
When designing our box, there is different things that we have to keep in mind. The requirements of the box were a 12-pound limit, a camera, temperature sensor, humidity sensor, air pressure sensor, GPS, battery. And on the right, you're able to see a digital drawing that we use to map out how we want to design our box. Actually, this is the box that we use itself, where we actually put in the Raspberry Pi and everything that we needed.
So with box assembly, we used foam boards in order to make our payload. So we used 2 6x6s, 2 4x4s, and 2 4x6s. Our first problem was if we were either going to use hot glue or super glue. We did a weight test where we basically glued 2 boards down, and then we saw how many newtons it took to break it, and super glue won. So that's what we used.
Testing and launching. Through this project, we are testing sensor calibration, indoor controlled drop tests, weight tests, final launch tests, and the weight tests on different adhesives.
Of course, we also have things to consider before launching, such as the time of day, the weather, the wind speed and direction, the launch date, and of course obstacles such as trees.
Before launch, we considered the following. We weighed our payload, measured the string, weighed the string, and filled our 24-inch balloons with helium. Then we did a neutral buoyancy test, which was where we took the mass of the payload and made a bag with coins weigh the same amount, And so we attached the balloons. And so basically we wanted it to be where it wasn't going up too high and it wasn't sinking to the ground. So it was just staying in the same spot.
So we first began our experiment by making a drop test, in where we basically simulated a weather balloon launch, but in a more controlled and a descending manner. We basically used our payload box and wrapped a string around it. We went up to the 4th floor of a tall building and we took it down. The entire thing took around 4 to 3 minutes, and we were able to gather some data.
We did this because we needed to calibrate our pressure to altitude system. Because we didn't have a specific sensor for altitude, we needed to convert from pressure to altitude. So as we were dropping it down, we were collecting the data, which we were then processing to give us a raw altitude.
After our drop test, we were able to plan our launch. We spent the last day working on the final tethered launch, where we debugged the microcontrollers, sensors, and cameras, assembled the box, attached the box and the microcontrollers to the 7 balloons, and sent the balloon into the air using a kite reel and brought it back down to collect its data. Here is our balloon on one of our launches. As you can see, it's a collaborative effort with everybody kind of working together and really helping this balloon get up.
After much preparation, we were able to do our first balloon launch. And although it was our first one and we heavily prepared, we obviously had a lot of challenges. The balloon was unable to successfully fly up, and it was sort of levitating on the ground. This led, which you can see on the graphs, just slight amplitudes between the pressure, between the altitude and the temperature. But this was a very good learning experience that we were able to apply for our next launch.
With our second balloon launch, we were able to fix many of our problems from the first try, and the balloon eventually was able to launch. We added another balloon, we reduced the weight, and it actually lifted off the ground. And while the balloon did begin to lift and even gain over 21 feet of elevation, unfortunately, one of the balloons actually popped due to the hot heat outside in the Texas weather, and that ended this attempt. As you can tell from the graphs, where it says balloon popped here, the altitude goes up and the pressure goes down, as that's a correlation, and then it very dramatically falls.
Our third launch was the most successful, with an altitude of over 75 feet, although it did not meet our goal due to the lack of balloon lift. Despite that, we received accurate and meaningful data that shows the connection between conditions and altitude. As we've seen in the graph, we see how the data was corrupted by winds as they pushed the balloon into the tree, as shown in the data.
Some of the challenges we faced during this project include the interconnection between all of the cameras, the microcontrollers, and the sensors, and the specific coding needed to power those sensors and take accurate data. Not only that, we were restricted to working on site because of the limited equipment that we were able to take home.
Also, with our launch, we had a couple of issues, being that, one, our payload weight required 6 balloons. It required a lot more than we actually expected. There's a lot of specific coding needed to go in place. There was a lot of wind. As you can see in the image, the balloons are flying horizontally, which led to our launch not actually going up very nicely as we thought. Heat, which led to some balloons popping, and overall, we did have some challenges, but we were able to overcome them and successfully gather some data.
Not only this, our entire project was made from scratch, and so all of the things we encountered, we had to encounter starting from the ground up.
All in all, we collaborated and assembled a high-altitude balloon to monitor atmospheric conditions during balloon launch. We also retrieved accurate data and analyzed to support our hypothesis.
We learned more in depth on the functions and capabilities of the Raspberry Pi and its coding, and we supported our own vitality of leadership, initiation, and collaboration.
In terms of future studies, Professor Noakes continues this project with his college students in order to analyze additional atmospheric data, assemble ground station and live data broadcasting, and use our payload to conduct extensive research.
So essentially what's going to happen is our progress that we've made, we're going to hand it off to Professor Noakes, and with his class, they're going to make the ground station and a couple of other things to make it so we can live stream the data from the balloon down to the ground station. Because right now what we do is we have our micro SD card and we have to manually read the data.
Hello, I'm Alexander Beckman, and I would like to major in mechanical engineering with a concentration in aerospace, and NASA STEM has really inspired me by giving me an opportunity to have practical research.
I'm Ella Brochu, and my career interests are mechanical engineering with a specialized research in aerospace engineering. The SEAS internship has equipped me with valuable research and knowledge that will take me one step closer to my dream of becoming an astronaut.
I'm Brian De Jesus, and I aspire to be a mechanical engineer with a concentration in aerospace engineering. And in terms of how the NASA STEM internship has impacted me, well, it's exposed me to an ideal engineering environment where I can actively participate in meaningful research. In addition, it provided me with a sophisticated outlook on what it means to be innovative.
Hi, I'm Jorge Hernandez, and I'm interested in being an engineer, but also a scientist. And this NASA SEAS internship has really inspired me by meeting all these professionals and fellow peers.
That was great.
My career interests are aerospace engineering, environmental science, linguistics, and international relations. The NASA SEAS internship program has impacted me greatly. It has inspired me to see myself in high positions within STEM by challenging me to be a better researcher and a teammate, by putting me in advanced scenarios with a high standard. It has also given me an opportunity to represent the first generation community.
Hello, my name is Anna Ravelis-Leon. I dream to be an aerospace engineer and hopefully one day be able to design spacecraft and lunar bases. SEAS has taught me the importance of building networks and take initiative, and also be a leader and persevere.
Hello, my name is Ryan Schaefer, and I want to be a mechanical or aerospace engineer. The SEAS internship has really impacted me because it's helped me hone in on aerospace engineering specifically, because before I didn't know what type of engineering I wanted to do.
I'm Raj Sinha, and I want to go into mechanical aerospace engineering. How has the SEAS internship affected me? It solidified my passion for aerospace and showed me that it's a real possibility in my future.
We wanted to give a special thanks to remote sensing scientist James T. Dietrich, aka Pi Guy, CSR Senior System Administrator Jim Pollard, aka IT Guy,
And the Eclipse team would be remiss if we didn't give a special thanks to Thomas Quattro-Hanover.
For making our NASA SEAS experience just as fun as it was academically empowering.
Thanks,
you.
Quattro.
We can't forget about our favorite high school senior peer mentor, Anchal Sabe. We are the NASA SEAS Payload Eclipse project, and thank you for watching our presentation.
So we remind you, if you have questions for the Eclipse team, please place them on the Slido app. Our first question is, do you think we want to invite all the participants on the team to please turn on their cameras and their microphones so you're prepared to answer the questions. Do you think Eclipse ballooning studies will increase well into the future?
I think that they will definitely. I hadn't had much prior experience with eclipse ballooning, but I saw how easy it was, and I was thinking about how it could really influence people's learning, like kids learning at a young age. So I think it would be a really good thing to implement in school systems because it is easy to do, and also with the invention of cube satellites, there are these really tiny microcontrollers, and they're super cool. They measure all these different types of things, but they're really small. So I think that opens up a variety of ways to do different ballooning than we didn't think of before.
The next question is about how long did it take your team to make the decision on what type of microcontroller you were using?
So it took our team about like 1 week to decide between Arduino and the Raspberry Pi. So basically our team had like knowledge with Arduino, so we knew like the whole pin diagrams, and we didn't know anything about Raspberry Pi. But a week later, we kept finding and like researching like the pin diagrams to translate all our knowledge from Raspberry to from Arduino to Raspberry. And as soon as that happened, we basically plugged in our camera, got all the sensors to work, and it was successful.
So the next question is, what were some of the challenges in designing the box?
So I think our biggest challenge was compatibility of all the sensors. Initially, our task was for the first 4 days to connect a camera to take visual data during the launch. And I mean, through trial and error, we weren't able to do it. And connecting all the sensors and getting them to interact with each other correctly, I think that was probably the biggest challenge.
And has anyone on your team ever seen a solar eclipse?
I know that many of our team has been able to see a solar eclipse. Me personally, the 2017 solar eclipse happened in 5th grade, and it was actually the first day of school. we were talking with my team actually, and I know that Alexander, Anna, and Ella were also able to see the eclipse. And I think just by seeing the eclipse, I think that's something that inspired me to go into this project and go into STEM as a whole, just seeing the impact that something like that could have on a nation and on students. Yeah.
How were you able to get the data off of the balloon to create your graphs?
So while during the eclipse, we planned to have a ground station to beam down live information and video. For our C's project, we actually saved the video onto a local drive. And afterwards, we used a Pi-based email system called Thunderbird to send ourselves the data and video files. But unfortunately, despite splitting the video files up into little 5-minute chunks, that email was actually incapable of sending the videos because they're really, really large files. So to receive the video, we actually used Google Drive instead to upload that and then re-download it on our computers at home.
And how does a tethered launch help you prepare for an actual launch?
Really, the tethered launch helps us just get all of the systems that we have to check down before an actual launch. So inflating balloons, double checking wind, location, all that sort of stuff. So just logistics of the operation.
What is the most important item that you believe needs to be corrected for a successful April 2024 launch?
For me, I think probably the most important thing would probably be the camera, because that'll let you see what actually is going on during the eclipse. And I know that actually seeing the video itself is very impactful for just seeing, like, having an impact and understanding what is going on. Like we stated before, we did have a bit of challenges with the camera with this project. So I think that's something that could be very much improved on, and that's essential for a successful launch, especially when the actual solar eclipse does come around.
And what is one thing that you feel your team might do differently if they were to do this experiment and research again?
So one of our biggest challenges, as we repeated before, is because solar eclipses is such a new topic that hasn't been researched before. The first week and the weeks following up, we were trying to research a lot about what our experiment was going to do and what we were actually capable of doing. So I think that now, if we were to do this experiment again, not only would we have the experience, but I think we would also value the importance of researching and asking questions a lot more. So we would be able to expedite a lot more and hopefully add more cameras, like an infrared camera. I know that we really wanted to do that, but unfortunately we ran out of time. So hopefully in the future be able to research a lot more.
So another question is, why do you think the temperature dropped at the end of the third launch?
So at the end of the third launch, our payload actually got stuck in a tree. And since where it was stuck in a tree, it was highly shaded right there. So the temperature began to rapidly drop since it was out of the direct 100-degree Texas sunlight.
And if your data was corrupted on the second launch attempt, how were you able to access all of your data and video?
So our data on the second launch, because of one of the balloons popping, was like the end of the launch, it didn't go as planned just because it eventually came down. But we retrieved the balloon and we were able to do a third launch. So the data was good up until that point. And then the first launch and the third launch, we could basically get the missing data from it.
Great. And our last question for the team is, what are the potential effects of high altitude radiation exposure on both living organisms and electronic equipment carried aboard a high altitude balloon?
So on these high altitude balloons, we're not sending any living creatures up, so there's no real effect on anything living. But on the electronics, there is a very real possibility of files corrupting. So one thing you can do to avoid that is you have your camera automatically split up the videos into 5-minute files. So if something does corrupt, it's ideally only like one file. So you have still some video. We didn't have time to do that, but that's one thing you can do to avoid negative effects of radiation at high altitudes.
Well, you've done a great job with your research, and I know that we all learned a lot. So thanks to the Eclipse ballooning team. We will continue our team presentations from our remote sensing team. The team used satellite remote sensing and imaging radar to observe the changing Earth with an emphasis on analyzing earthquakes. So please welcome the remote sensing team presenting imaging large-scale earthquakes using INSAR.
Hello, we are the remote sensing team. For the past 2 weeks, we have been working with the NASA STEM high school internship program with the project of processing INSAR data to image large-scale earthquakes.
Hi, I'm Nalini Agnihotri. I'm a rising senior at Coppell High School, and I live in Dallas, Texas.
Hello everyone, my name is Pablo Echeverria Cuesta. I'm from New York City, and I'm a rising senior at Lycée Français de New York. Hi, my name is Raj Matar, and I'm from the Woodlands, Texas, and I go to the Academy of Science and Technology as a rising senior.
Hello, my name is Gia Michelle, and I'm a rising 11th grader in New York City at St. Anne's School.
Hi, my name is Pearl Iwale, and I am a rising 12th grader at William P. Clements High School in Sugar Land, Texas.
Hi, my name is Marisa Galchot. I go to Cypher High School in Houston, Texas as a rising senior. Our mentor for this project is Dr. Ann Chen, who is an assistant professor at the University of Texas at Austin. She currently leads the Radar Interferometry Group in the Center of Space Research. So, what is remote sensing? In a broad sense, remote sensing is the technique of acquiring data from a distance. This can be done by planes, satellites, drones, etc. For our earthquake interferograms, we use satellite remote sensing. Satellites can use a variety of sensors to acquire data, such as cameras, radar, and LiDAR. Using cameras is beneficial to get high-resolution images that can show vegetation and infrastructure, but they cannot pass through clouds. Radar can. Radar scans the Earth through means of microwave rays, and LiDAR uses laser altimetry to scan the Earth's surface. We will use the radar sensors to acquire our data. In the top image, there is a SAR image over the San Francisco Bay Area, which is by means of radar. The bottom image shows the same area, but taken by a camera.
Synthetic aperture data, also known as synthetic aperture radar, SAR, is a remote sensing technology that uses radar signals to capture high-resolution images of the Earth's surface. Now, unlike optical sensors, SAR operates in the microwave region, enabling it to function day or night and penetrate through clouds and vegetation. Its all-weather capability and wide area coverage makes it valuable for applications such as environmental monitoring, disaster management, agriculture, and even defense. INSAR stands for Interferometric Synthetic Aperture Radar, a technique used to measure ground surface deformations with high precision. It involves the use of multiple radar images acquired over the same area at different times to reveal topography or surface motion. By comparing the phase differences between these two images, INSAR can even detect subtle ground movements such as subsidence or uplift caused by various geological or human-induced processes. Processing the deformation can allow researchers to analyze surface roughness. An interferogram shows what INSAR does. The first pass consists of the reference phase, while the second pass measures the phase again. The role of the satellite is to measure the difference in the phase in order to determine the deformation in a given time.
Although we had difficulties with processing, we were able to compile images through these 5 simple steps on both Windows and Macs.
There are 5 main types of satellites. Satellites can vary based on their orbit. Some orbits like the ISS have low Earth orbits that take 90 minutes to circle the Earth, while satellites like Galileo have medium orbits which can take up to 24 hours. Geostationary Earth orbits like Intelsat align with the Earth, while sun-synchronous orbits such as RadarSat correspond to the time it takes for Earth to revolve around the Sun. Geostationary transfer orbit is slightly different because it orbits a planet only as an intermediate step before launching to its final destination. A great example of this mission launch is the Ariane 5 launch.
LiDAR and INSAR are two technologies that are crucial to remote sensing. Although they may seem quite similar from an exterior point of view, especially because they are both used at all times of the day, they are both quite different. LiDAR can be used in all weather conditions and can surpass most clouds, but it covers a single line of data. On the other hand, INSAR covers much larger areas in 2D, so it's much quicker. INSAR tracks deformation while LiDAR tracks elevation.
With the many available radar missions launched by the global space agencies, we had an ample amount of data that we had access to through the Earth data. However, due to the constraint of using a personal computer, which cannot efficiently process large amounts of data, and the fact that earthquakes occurred during the decade of 2010, we chose ALOS PALSAR data sets to visualize earthquakes and analyze the amplitude and phase.
Excitingly, NISAR, a collaboration between NASA and the Indian Space Research Organization, is planned to launch in 2024. This is the first satellite to use two different radar frequencies, L-band and S-band. L-band frequencies can work through vegetation, while S-band is used to monitor soil moisture. Deformation is able to be visualized through processing the ALOS pulsar's phase. A fringe refers to a color-to-color segment, representing 12 centimeters. Once you count all the fringes, you can see how much deformation there was.
SAR amplitude is measured by the return energy of a particular pixel, which is essentially like the measurement of strength of the radar response pulse that is backscattered. Amplitude can be impacted in a variety of ways, such as terrain, roughness, and vegetation. Basically, the greater the amplitude, the stronger the signal, which often means if an area shows up darker on a map, that means the area is super flat, and it's lighter as the opposite.
The 2010 Chile earthquake was one of the most drastic tremors of the decade. Even though it only lasted 3 minutes, the repercussions and the recovery efforts took over 4 years. The damage incurred more than $30 billion losses and destroyed many homes while taking hundreds of lives. As evident in the phase diagram, the phase was superimposed onto a Google Earth terrain and consists of a multicolored set of fringes. This shows that the epicenter is near the coast of Chile and that the earthquake was very severe in magnitude. The amplitude describes the terrain on the grayscale for further analyzation. Because the aftermath was so drastic, remote sensing would have been extremely beneficial to citizens for better destruction preparation. They would have also been able to understand where the fault occurred for better first aid care in the future. In response to the damage, citizens made improvements to the city by updating building codes with strong columns and weak beams. Buildings would now have a better chance of swaying with the tremors rather than collapsing to them.
In 2010, Haiti suffered a 7-magnitude earthquake, killing 250,000 people. Although scientists originally thought it was from the Enriquillo fault, through data visualization, they understood that it was actually due to the Leogan fault. Here you can see the differences.
An earthquake occurred in 2009 in the Italian city of L'Aquila. 308 people died, making it one of the deadliest earthquakes in Italy since the 80s. You can see the earthquake in the bottom left of the phase imaging. So, what could tracking earthquakes like the 2009 L'Aquila earthquake tell us? It's sort of a fascinating story. After the disaster, members of the Italian National Commission for the Forest and Prevention of Major Risks were convicted for downplaying how extreme the earthquake would actually be. They said things like, an earthquake of this size in California would not cause any harm, but clearly it did. There are probably a lot of other factors that led to such devastation, such as maybe modern buildings that were not up to code. So those were also kind of the subject of such criticism.
In 2010, the Salta province suffered a 6.7 magnitude earthquake, killing 2 people. Originally, they believed it was the result of the Chilean earthquake. However, the data proved differently. Unfortunately, the data that we downloaded was not able to confirm that these were fringes of an earthquake, as they actually may be a result of orbital errors.
The devastating Christchurch earthquake occurred in New Zealand on February 22, 2011. The earthquake had a magnitude of 6.3 and struck the city of Christchurch on the South Island, causing widespread damage to buildings, infrastructure, and resulted in the loss of 185 lives, making it one of the deadliest earthquakes in New Zealand's history. The earthquake's impact was particularly severe because it occurred close to the city and at a shadow belt, amplifying the shaking and causing significant damage to many buildings that were already previously weakened by an earthquake in September 2010.
This earthquake occurred in Yushu, Shanghai, China on April 14, 2010. The epicenter of this earthquake was on the Tibetan Plateau. This area is regularly hit by earthquakes and is sparsely populated. 2,698 people were confirmed dead, 270 missing, and over 12,000 were injured. The magnitude of this earthquake was 10.1. The dense vegetation and mountainous regions likely interfered with the resolution of this interferogram. This explains all the noise shown in the grays area. This also hints towards potential room for improvement in future interferograms. This earthquake struck in October 2008 in Osh, Kyrgyzstan. The center of this earthquake was near the village of Nura, around 140 kilometers from Osh. 75 people were confirmed dead, including 41 children, and 150 were injured, including 93 children. The magnitude of this earthquake was 6.6. Despite the high magnitude of this earthquake, it is probably a deep earthquake, for the surface does not show severe deformation.
Located in China, on October 6, 2008, there was an earthquake of a magnitude 6.4, which resulted in 10 deaths and 11 serious injuries. In the area located in the circle is where the epicenter of the earthquake should appear, but due to rigid terrain, the fringes of the Earth do not appear on the interferogram. It's quite frequent that sometimes interferograms cannot detect an earthquake due to various reasons like magnitude or terrain.
So this is an earthquake from Mentone, Oklahoma. Oklahoma's induced seismicity has been occurring a lot more recently in the region and its surrounding states such as Texas and Kansas. This earthquake that was the result of induced seismicity is associated with industrial processes such as geothermal energy extraction, mining, dam building, construction, and hydraulic fracturing. But as for the large amount of recent swarms in Oklahoma, they're often the result of injecting into wastewater wells. As you can see here, although the area is not very terraneous, it's very flat, not very forested, we were unsuccessful in finding an earthquake, and I believe that this is due to the small magnitude of the earthquake. It is only a 4.3. Current technologies have limitations in how small of an earthquake they're able to detect. But you might notice that there are large blocks of colors such as blue in some areas, but that's just tropospheric noise.
Tsunami risks. 5 to 10% of earthquake-caused tsunamis are from silent earthquakes. The difference of a silent earthquake is that the movement of the tectonic plate is much slower, taking hours for a change to be noticed, unlike the usual few seconds. Although slow, debris in form of a landslide can still quickly fall into the ocean and cause tsunamis. 1992, Nicaragua, a tsunami killed 170 people and left 13,000 homeless, which was caused by a silent earthquake.
Kilauea volcano in Hawaii released the energy of a magnitude of 5.7 in response to 2,000 cubic kilometers moved towards the ocean. However, this was unknown and recognized by all, even seismologists. This took an extensive 36 hours, but when someone finally noticed, Kilauea's south flank shifted 10 centimeters, equivalent to a bagel. But this does not mean that the results are not deadly. If the debris on the volcano gained momentum and formed a landslide, it would cause destruction. Silent earthquakes can predict flank collapse, which is basically the side of a volcano collapsing. Through GPS measurements and remote sensing, scientists are able to track that silent earthquakes are discrete. When it comes to seismic measurements, they are able to also understand that they happen regularly in a pattern, so they are predictable. So when seismic gaps, such as those that happen in Japan, happen, scientists are able to understand that this could actually be due to the fact that there are silent earthquakes occurring, not that there is an active degree of destruction that will happen in the future. Remote sensing allows for people to understand and predict things that are often misunderstood.
There are already a lot of important usages for interferograms. One example of some future usage that we plan to implement is a classification system utilizing machine learning in order to recognize patterns. As you could see from the various interferograms we created throughout this internship, some were easy to detect and some were not. Our classification system could be used to predict whether or not a future earthquake could be detected using an L-band interferogram, which is what ALOS, the satellite we got our data from, uses.
Without the radar images, we might still be wondering what happened, said geophysicist Eric Fielding. Through using INSAR, we were able to accurately and precisely analyze some of the most devastating earthquakes over the past few decades. Remote sensing is a powerful tool that allows us to look at our changing world and gives us the tools to potentially help save lives.
So we all had an amazing time at our SEAS internship. So some of the best features that we all experienced was research experience, of course. We all got the opportunity to research, we got to meet with like-minded students, and we got to work and learn from amazing mentors while learning about new fields and careers. But we did have our challenges. Some challenges were time management, which were often independent, but they're also just, we have a lot of activities and work that we have to get done in the span of 2 weeks. And then the second challenge would be getting out of our comfort zones. We're going to be meeting new people, learning about a lot of new things, so oftentimes we have to get out of our comfort zone a little bit. And the last challenge we faced was using new software or using new technologies or techniques to process data. Oftentimes it came with its challenges.
I am someone who loves chemistry and plans to pursue chemical engineering in college. Through SEAS, I've actually grown a new interest to continue to graduate school to study material science and hopefully help with the design of spacesuits for astronauts. I also feel more confident going into college after multiple guest speakers who are extremely successful gave wonderful advice to be resilient and to never give up even when your plans don't go according to ways.
Okay. Attending the NASA STEM Enhancement in Earth Science internship taught me that there are so many fields of technology, science, and math that are codependent, and the opportunities I have for my interests are endless at this point. Prior to attending this internship, I felt very rigid about what I could and could not do with certain majors, but I learned that there's so many different fields and subjects that are necessary to complete a project, knowing earth science, physics, and chemistry. Working with a team as well for the duration of this internship taught me a lot about compromise and respect, and I was really glad to meet everyone. Because of my work with environment and satellite imaging, I am considering combining my passion for technology and computer science with environmental research in my future career.
I have recently developed an interest in astrobiology when I came to the realization that the major was the combination of my deep interest in technology and medical science. SEAS not only allowed me to pick up a new skill of processing and analyzing data, but it also inspired me to learn more about space biology and earth science through various guest speakers, passionate mentors, and willing people to just guide us along the way in further research.
From connecting with other high school students focused on varying fields in the STEM industry, to learning from experts in their field, NASA SEAS is a truly one-of-a-kind internship. Expansive research that impacts the whole world and maybe the universe. And I am so glad to have been given this opportunity.
The SEAS 2023 internship has been a great learning opportunity. I've learned to work in groups, and I've learned what research really means. No matter what I do in the future, I know that I will pursue engineering for the purpose of sustainable development.
Before the NASA SEAS high school internship program, I was nervous to select a college major. I learned that some of the biggest problems facing Earth require many disciplines. For example, the remote sensing project I worked required researchers from many fields, such as environmental sciences, electrical engineering, and computer sciences. I learned that no matter what specific field I choose to study in college, I can still. On behalf of our team, I would like to thank all SEAS staff and mentors, especially Ms. Miller, Ms. Baggio, and Dr. Chen. And thank you for everyone for listening to our presentation.
Wonderful. So we have several questions that have been posted. So we invite the remote sensing team to please turn on their cameras and their microphones. The first question is, what are the most promising ways this technology can further contribute to climate research and aid in mitigating the effects of global environmental challenges?
That's a great question and so relevant. So we discussed a lot of the different satellites that have been used for remote sensing. And one that we did not discuss was ISAT, which was we talked a lot about during the time at NASA SEAS, which actually tracks the way that the water and ice is melting. And also there are satellites like GRACE that also track like ice melting. And for example, ALOS Pulsar and all of these other satellites allow us to understand how the climate is changing. So researchers, scientists, politicians, legislators are able to use all of this data to understand how we can make an impact on the climate crisis in the future. And it's a really very part on tackling climate change.
What is the potential of remote sensing-based real-time earthquake monitoring systems for early warning and disaster preparedness?
Although through the research that we have done in these past 2 weeks, we are not able to use that research to understand the potential or predict, we can use remote sensing data to understand patterns, like we discussed with silent earthquakes. And also we hope to create a classifier in the future that uses machine learning to understand further patterns with earthquakes.
How do you feel remote sensing bridges data gaps in remote regions and provides insight into seismic activity? And then also, what are its limitations?
So I believe that remote sensing bridges gaps for areas that are hard to access, because when you create an interferogram, you're able to use satellite data over remote regions over longer periods of time. And for example, like in Haiti, there's a lot of regions of the island that people could not go to survey and assess the damage and the impacts of the earthquake via seismographs and other sensing techniques. So by using satellite data from a distance where we're able to assess the actual impacts of the earthquake on the region and the land, you're able to provide accessible information and data over a region or area that is not accessible normally.
And another question is, what do you feel is the most important reason to use remote sensing?
So with the increasing issue of climate change and its prevalence in our current day, remote sensing gives you a really, really wide grasp of the land because of the satellites, and the repetitive motion of it allows us to be able to track different signs of climate change. So you can now look at different glacial damage and coastal reclining, along with surface geology and vegetation differences.
How do you see remote sensing's potential impact on various industries? And what are the key challenges that need to be addressed to fully leverage its capabilities?
I think that remote sensing is going to be very important in spreading awareness. That's the big one. So for instance, remote sensing, based on different wavelengths of the satellites, can help track, for instance, tornado scars or tracks of wildfires. So it's this information, although we know it's occurred and all we have is a scan of it, it helps us understand, for example, how a certain forest can regenerate. And so this is going to be helpful in the future. And yeah, I think it's mostly going to spread awareness on our impact on the planet, and then also how the planet reacts.
Great. How can remote sensing technologies like INSAR and GPS interferometry be synergistically used to analyze earthquake spatiotemporal characteristics?
That's a great question. So in regards to the GPS, the satellite we've been using mostly, so ALOS Pulsar, uses GPS, which helps us determine its exact location, right? And so how is this helpful? This helps us have a higher resolution. So if we know where the satellite is exactly, we know what it's looking at, we can also determine the angle, and it helps us determine also, for instance, say you have a mountain, the angle it's looking at, and yeah, so it helps with the amplitude and the just overall the high resolution of the interferograms.
Yeah,
Great.
and I want to also comment here. So, so the satellite use the GPS to do orbital determination, but also there are permanent GPS stations on the ground that record how surface moves. So I would say INSAR and the GPS are complementary. So INSAR has a high spatial resolution, but it measures the motion in line of sight, while GPS give you point measurement, and the density in some of the tectonic active region is quite dense, but in a lot of the areas sparse, give you 3D deformation. So they're kind of considered as independent measurement, and so you can use GPS to validate the INSAR and also have more confident for mapping surface deformation using INSAR in area where the GPS validation is not available. And I think one of the most important things is while both INSAR and the GPS both measures the surface deformation, those deformation patterns have very, very rich information about the Earth's subsurface, which is very hard to measure. And to be able to understand the fault geometry, fault depths is actually very important to understand the overall seismic activities and future risk. And it's been great pleasure to work with the team.
So great job to the remote sensing team. Our next presentations are by interns in the Galaxy Classification Group. Our Earth is just a small part of the whole universe. In addition to learning about the scale of the universe, students contributed to astronomy research through citizen science projects. While helping astronomers process vast amounts of data, students identified and classified galaxies. A special thanks to project mentor Dr. Judith Reese for her commitment and dedication. So here is the Galaxy Classification Group, and their first team is utilizing morphology distribution of galaxies as a function of redshift. So please welcome the Redshift Wranglers team.
Hi. We're the Galaxy Classification Redshift Wrangler team. I'm Connor Wolf.
I'm Cassius Bermudez.
I'm Lorelei Lovell.
I'm Malik Perez. The primary focus of our research was centered around the evolution of galaxies over time. We hypothesized that irregular galaxies were more common closest to the time of early galaxy formation. This is because galaxies were closer together and therefore interacted more often. To study the older galaxies, we analyzed the data from the Redshift Wrangler citizen science website to calculate galaxies redshift and record galaxy type. We additionally used data from the SDSS catalog to study younger galaxies. Redshift is a phenomenon that occurs when looking at an object that is moving away from us. The light coming from most galaxies elongates, which means that it's moving toward the red side of the spectrum. By observing the redshift of galaxies throughout the universe, we can see that they're moving away from our own galaxy. Hubble was the first to observe this. The light he was able to capture and analyze appeared to be redshifted. This observation led us to believe that the universe is expanding. Higher redshift typically indicates older age in an object, while a lower redshift indicates a younger age. On this slide, we have Hubble's diagram. It describes distance versus redshift. The data comes from a supernova survey conducted by Hubble. Objects plotted on the right side have a higher redshift, which indicates an older object. This is the first observational evidence we have ever had of a rapidly expanding universe. The first line of the graph of the universe represents 30% matter and 70% of some mysterious substance, which we call dark energy. The second line demonstrates a universe where there is 30% matter and nothing else. This one is quite difficult to interpret because there is nothing within the other 70%. Yet what is interesting about that is it still fits the data better than the next line. This third line shows that it would look like what it would look like if the entire universe was fully made of matter and had no dark energy. The fact that the first line, the one with 70% dark energy, fits the data better than the other two leads us to believe that there's something causing the expansion of the universe, which we now call dark energy.
Galaxies are classified into many categories, including giant elliptical, dwarf elliptical, spiral, barred spiral, and irregular. When looking at the data, we classified the galaxies into these categories to find the evolution of them by observing their redshifts. This allows us to observe the types of galaxies we think formed in the early stages of the universe. However, due to many of these objects being over 10 billion years old and lack of resolution from the Hubble telescope because of distance, it often becomes difficult to determine the shape of many of these galaxies.
Quasar is derived from the word quasi-stellar, which means star-like. This is because when first photographed in the 1950s, they looked faint and had the resemblance of stars. However, this star presented scientists with some confusion. It had a redshift of 0.158, which at the time was massive and very hard to believe. If this was true, it would mean that quasars are so bright that they outshine all stars and the Andromeda Galaxy. Now we know that this is true, and quasars are associated with galaxies in the nucleus.
Hydrogen emits and absorbs light at certain wavelengths as the electron jumps into shells of different distances from the nucleus. The spectrum of emitted and absorbed light can be seen on the right. The lines in the spectra represent the specific wavelengths at which hydrogen emits and absorbs. Since this property of hydrogen is constant throughout the universe, we can use these lines to gain information even about the most distant galaxies.
We took 30 galaxies from the Redshift Wrangler Citizen Science and identified their emission lines, which are boxed in red, and absorption lines, which are boxed in blue. Since we know the original hydrogen emission lines and where the observed emission lines are, we determined how shifted the light was using the equation on the right.
To find high redshift galaxies, we used the Redshift Wrangler Citizen Science Project to analyze galaxies that were photographed by the Hubble Space Telescope and used spectra collected from the Keck Observatory. We used the two plates from the SDSS, which also had galaxies that had a redshift of up to 9.
As seen in the figure, we found that irregular galaxies as a percentage of total galaxies were most common at higher redshifts, but their frequency dropped at very high redshifts. We had very few data points in that range, so that might explain this effect. Elliptical galaxies, both dwarf and giant ones, were more common at lower redshifts. Giant elliptical galaxies are believed to form due to galactic collisions between irregular and spiral galaxies, which can be explained with our results, as giant elliptical galaxies may not have had time to form in the early universe. Quasars, both by percentage and by number, were more common at higher redshifts, especially redshifts near z is equal to 3. This finding is likely due to the fact that quasars are especially bright, which means they're easy to find even when they're very distant, and the fact that the younger universe had more available gas to fuel more quasars. Correlating galaxy type with redshift confirms that irregular galaxies and quasars were more common in the early history of the universe. Future studies from the James Webb Space Telescope could provide more data for very distant galaxies and quasars to improve statistics at high redshifts.
SEAS was a great opportunity for me, and my favorite part was going to the Johnson Space Center and seeing the mock-up of the ISS in the Neutral Buoyancy Lab.
I'm incredibly grateful for the opportunity to have participated in the SEAS internship, where I was able to gain invaluable experience and learn from some of the brightest minds in the field of STEM. The work we have done helped me to grow in a hands-on environment, which is something I don't get often in a classroom setting.
SEAS has helped me learn new important topics in relation to STEM, and I'm glad to have this opportunity. It also allowed me to create new friendships, and I am happy that I learned what Redshift really is.
SEAS had been a once-in-a-lifetime experience that allowed me to explore my interest in science and meet truly incredible people.
Here are some pictures of our time at SEAS. We would like to thank Dr. Rees for teaching us all of her knowledge about astronomy and redshift. We would like to thank Bob Twiggs for his incredible generosity in letting us use his Z-cubes. We would like to thank Dan Tanney and all the other presenters for teaching us about what they do in the STEM field. And lastly, we would like to thank Miss Margaret and Miss Selena for making everything work at SEAS.
So we had several questions for the team. We invite Connor, Cassius, Lorelei, and Ayla to turn on their cameras and their microphones. And our first question is, how did you choose the galaxies that you used for the data?
So we used two different plates from the SDSS, which is a collection of galaxies that are sorted. And originally, we just used galaxies at a certain place in the sky, but in order to gain more data, we just used the full data set provided. So it was essentially a random sample.
Why is the Hubble's original distance redshift graph is considered so important?
That's because we originally thought that the universe was static, and Hubble's observation of the redshift it allowed us to see that the universe was actually expanding. And it was also like we were able to see how distance and redshift are related to each other.
Have any of you researched galaxies prior to this internship?
For me in particular, no, I haven't, but I was definitely really interested and intrigued with what I was able to learn about the redshift, because prior to this, I did know that the universe was expanding, but I didn't really understand fully how we knew that. And looking at redshift, it really showed us how the light switching to the red side of the electromagnetic spectrum from these galaxies shows us the rapid expansion of our universe.
Was there a difference in the data that you saw from Hubble and new data from the James Webb Telescope images?
We didn't have access to James Webb images, so that limited how far we could look back into the universe. Because Hubble has less resolution, it was harder to see and find the very, very distant galaxies. But we did find that the more distant galaxies had a higher frequency of irregular galaxies and quasars. And we'd imagine that if we had James Webb telescope data, that trend would bear out. So that'd be some future research we could do.
So were any of you interested in astronomy as a possible career prior to SEAS?
Yes, I was interested in astronomy. I was deciding either if I wanted to go with like astronomy or astrophysics, because I haven't really learned too much about physics yet. So that was definitely two paths that I definitely wanted to consider going to major in college.
So then did SEAS change your career path or reaffirm your passion?
It definitely opened my eyes more to like the engineering aspect. So that is definitely something that I might consider in the future. However, when doing my research, I was really interested in our redshift data. So I think that also has, I guess, boosted what I wanted to do in astronomy or astrophysics.
As you were conducting your research, did you feel that that identifying and classifying galaxies is more on an individual basis, or were you able to work in a team setting to share ideas and examples as you came up with results?
I think there were some parts that were mostly individual, where we would just go through each galaxy. We'd each take a portion of the galaxies and we just enter the data into an Excel sheet. But then there were also parts where we each focused on certain areas. So maybe some people would be collecting the data and the other people would be putting it into graphs and analyzing it. So there's sort of both individual work and working together.
Great. Well, you've done a wonderful job with your research, and our thanks to your team. So we will continue with team presentations from Galaxy Classification Group. The next presentation is Searching for Galaxy Cluster Candidates from High Redshift Galaxies.
Hello, my name is Sydney Walker.
I'm Anna Grace Aiello.
I'm Landry McRoy.
I'm Brooke Quintana. And we're part of the Galaxy Classification Dark Energy team. Today, we will be talking about searching for galaxy cluster candidates from high redshift het-dex galaxies.
When examining this, the first question we have to ask is, what is dark energy? The short answer is that we don't know. We know that it can't be directly observed, but that it's everywhere, making up approximately 68% of our universe. We know that it's needed to explain why the expansion of our universe is accelerating rather than being overcome by gravity, slowing and eventually beginning to collapse in upon itself, but we don't have a precise definition.
We do have some ways of finding it. Dark energy is really just how the universe expands, and we can observe that through supernova, distortions, and sound waves. Some exploding stars that are known as supernova were observed to be fainter than expected. The explanation for the difference in expected light led scientists to believe that the universe is expanding faster as it ages. Type 1a supernova are instrumental to understanding the expansion of the universe. The destruction of a white dwarf star is fairly predictable, so by measuring the observable brightness and the true brightness, we can find the distance of the supernova. We then measure how fast the star is moving away from the Earth by evaluating the redshift, the stretching of light waves caused by the expanding universe. As light waves travel throughout the universe, they get warped by the gravity of intervening objects. This is called gravitational lensing. A weak lensing produces a subtle distortion in the shape of a galaxy, an effect that could only be observed through the analysis of millions of galaxies. Such patterns map a three-dimensional chart of the distribution of matter throughout the universe. Dark energy causes the space between matter to get larger, thus causing the expansion of the universe and the distribution of matter to be thinner. Different theories for dark energy require different histories of expansion to occur in the universe, and so the determination of how the universe has expanded will assist in the determination of the correct theory on what dark energy is. We also look at sound waves measured by het-dex. Sound waves originating from the dense early universe helped matter begin to clump together. The technical term for these sound waves is baryonic acoustic oscillation, and can be considered as the basic measuring unit of the distribution of matter in the cosmos. The more waves of pressure in an area, the more stars and galaxies will form in that area. Scientists are able to search for signs of these sound waves with het-dex in an attempt to find the imprint of these ancient sound waves. By measuring the imprint of these sound waves and comparing them to the relative strength of dark energy at different epochs, being the speed of the universe expands, we can assess what dark energy truly is.
All our data from this project comes from the Hobart-Eberly Telescope Dark Energy Observation Project, or het-dex, at UT Austin's McDonald Observatory. It surveys over 1 million non-targeted galaxies, and every exposure produces approximately 34,000 spectra. The thing that makes this so exciting is just how much data there is and how old it is. That creates a problem. There's too much data to be processed, and so scientists at UT Austin are relying on citizen scientists to help start to process it and train an AI algorithm to do the same.
Citizen science is so important because the massive amount of data necessitates participation from volunteers. This also allows qualified scientists to spend more time on pressing issues. Dark Energy Explorers, the platform we used, has collected approximately 1.3 million classifications, has 14,124 volunteers, has reached over 85 countries, and is 91% complete with the het-dex dataset.
To explain how we understand and classify these galaxies, you're going to have to look at the image to the right. Each signal is a composite of several spectra tiling a circular region of the sky. Each colored box contains a small part of the spectrum where we have detected a signal. The black dots are the signal, while the gray background is noise. These dots are photons that have been traveling for up to 11 billion years, coming from a galaxy that's producing a lot of stars, and they finally made it into our instrument. The top left box in the black outline is the sum of all the colored boxes. The more clear and strong the dot appears in this box, the better we trust the signal. Additionally, it's important to see signal in individual fiber spectra. If we see dots in two or more of the colored boxes, we have high confidence that the signal is real. The boxes in the upper right show optical fiber positions. The bottom left box displays resultant 1D spectrum and emission line fit. It shows redshift and distance. We use spectral lines to determine if an astronomical object is real or fake, fake being its noise from the telescope or other instrument. Spectral lines are often used to identify atoms and molecules. A shift in the position of the spectral lines in our data tells us the distance to the galaxy, so we can create a three-dimensional map of the night sky. The brighter the yellow dot in the line flux map, the more likely the galaxy is real. A yellow line, however, displays the data error.
Part of our research involved taking our own part in citizen science. To sort through HETDEX data, we distinguish between background noise, bad data, galaxies, and black holes. While looking for bad data, we looked for missing sections of optical fibers. You can see in the first image, there are missing pieces of data that look like small gray rectangles. Bad data is also identified by repeating sections in the line flux map or within the fiber images. It's easy to identify because it almost looks like a glitch in the image. While identifying galaxies, we are looking for a clear circular or ovular shape in at least two of the fiber images. You can see in the middle image, there is a clear circle in the combined fiber image. While looking at the smaller fiber images, there's clear evidence of the shape of the galaxy because the dark figure shows up in multiple slides. Taking a look at the spectral lines, there also must be a clear correlation between a line of best fit and the spectral lines. In the line flux map in the bottom right corner, there must also be a clear yellow dot within the red square. If you're lucky enough to see a black hole, you'll see an elongated black shape in the optical fiber images. The spectral lines will usually follow an elongated curve, but in the ones that we found, the curve ended up being taller with less area. When you don't find bad data, a galaxy, or a black hole, the data is most likely background noise. There will be no clear dot in the optical fiber images or in the line flux map, and the spectral lines will not follow a clear curve. If none of the criteria for galaxies or black holes apply to the image, it is most likely background noise to throw back into the system. In only a couple hours, we sorted through a total of 2,140 data points. We discovered 899 galaxies, which is also equivalent to 42% of our entire data set. We also discovered 4 black holes, equivalent to 0.2% of our entire data set. The rest of our data was background noise or bad data, which we had to throw back into the system. This is why citizen science is so important. As a team of 4, we were able to sort through over 2,000 data points in only a few hours.
In addition to citizen science, we analyzed 139,188 galaxies from HETDEX Source Catalog 1, separated into 6 different declination ranges. Declination is the celestial equivalent of latitude. The full dataset included over 200,000 objects. To narrow down this massive dataset, we removed all stars, as well as galaxies, with a redshift confidence of below 0.4. What we're looking at with this data are high spectroscopic redshift galaxies of Z equals 1.9 to Z equals 3.5, meaning that they're very old and very far away. Currently, the farthest known galaxy cluster is located at a redshift of 2.5, and the farthest supercluster is located at 1.27, and we're looking way beyond that. The first image we have is a 2D polar graph of all 140,000 galaxies. Because we couldn't model in 3D, we examined these galaxies separately in 2 planes. We start here with groups of declination. The circular rings you can see radiating outward from the origin are different redshifts or distances, which were multiplied by a factor of 10 for graph simplicity. The straight lines stretching outward are different right ascension angles, which are the celestial equivalent of longitude. You might be wondering about the blank spaces within the graph. Since this data is from 6 years into the 8-year survey, some parts of the sky have not been explored by HETDEX. Additionally, low confidence galaxies as well as all stars were removed from the full release dataset. Here we have a zoomed out graph of declination group 6. It has very few points, less than 1,000, so it's too hard to identify any clumping in this graph. Let's skip past it. Let's take a closer look instead at declination group 4, which are 52 degrees to 54 degrees. Here is our zoomed out graph. The dark, dense black triangle near the origin is relatively nearby galaxies with low redshifts that have already been studied. We're focusing on the outside section, about 1.5 to 3 on this graph. Recall that these numbers have been multiplied by a factor of 10 for simplicity. Here is our zoomed-in model of declination group 4. The red circles surround visually identified clumping, and the lines through them are different right ascension angles. The top right ascension line on this graph has a considerable number of possible clusters, so let's investigate it further. We will use the inverse tangent of the green point and add 180 degrees because it's in the third quadrant to find that this line is at an angle of 214 degrees. Now we double check that this is indeed a clumping by flipping our graph. This graph is grouped in a range of right ascension centered around our previous calculation of 214, and the red line is a line of declination. We will use trigonometry once again to find the angle of this line at 52, which falls exactly within the group 4 declination that we originally found our 214-degree right ascension at. This proves that there is indeed a galaxy cluster candidate at the celestial coordinates of declination 52 degrees and right ascension 214 degrees. However, we can't know that this is indeed a cluster without analyzing other variables, such as velocity dispersion and density. We have checked the x-plane and the y-plane, so we have one last step to verify that this is a cluster candidate. These graphs show the distribution of galaxies in the sky grouped by redshift. Redshift is the distance, so it would be the z-axis of our hypothetical 3D graph. The center point for each graph is 214.52, our celestial coordinates, in arc minutes. These images show why we need more refinement in our search. We still see clumping around these coordinates, meaning that we were very close to the right numbers, but not exactly on the dot. With further research and greater computational abilities, we can ideally get these coordinates down to the decimal.
I studied declination group 1, which was a group of galaxies with a declination of -5 to 5 degrees. I found clusters with a right ascension angle of 20 degrees. Once I found the other groups of galaxies with a right ascension angle of approximately 20 degrees, I found that they all fell into a declination of about -0.23 degrees. Realizing that this fits into the original dataset with a declination of -5 to 5 degrees and finding clumps along the declination plane, I was able to prove with little doubt that these galaxies are potential candidates for galaxy clumps. It is important to keep in mind the right ascension angle goes in a 360-degree counterclockwise circle, and the declination is in a range of 90 at the North Pole to -90 degrees in the South Pole, with the celestial equator being at a 0-degree declination. With this declination being about -0.23 degrees, this data set is right in line with our equator.
There is reasonable evidence of galaxy clumping candidates at high redshift galaxies, such as 1.9 is greater than z is greater than 3.5, from the Hobby-Eberly Telescope Dark Energy Experiment, also known as HETDEX survey. It is based on visual observations of clumping from 2D polar graphs of declination ranges and right ascensions. Over 30 possible clumpings were identified within the right ascension equals 20, declination equals 0.05, and right ascension equals 196, declination equals 54.5. Once again, it must be mentioned that we currently do not possess the computational power to validate these galaxy clumps, and these are merely candidates. Our experience.
My experience here at NASA SEAS in UT Austin has been once in a lifetime. In addition to forming close friendships with some seriously stellar people, I've loved performing unique research on dark energy in far-off galaxies, something truly out of this world for a high schooler to be able to experience.
This experience has honestly pushed me to grow like nothing else. Every day I've come in to work with a ludicrously talented group of students. And even if we haven't been explicitly taught how to handle what we're doing, we know that we can figure it out, and that process will teach us more than any classroom setting.
This experience gave me an incredible opportunity to work with like-minded individuals on a shared interest. It opened my eyes to the field of astronomy too. I feel that I've not only gained technical knowledge on the subject of space science, but I've gained experience collaborating with interdisciplinary STEM focus groups.
My time at SEAS was an excellent opportunity to grow as a person and as an academic in a new and competitive environment. Being able to listen to experts in the industry about their work, the paths they followed to get where they are today, has been an incredibly useful tool and will be for more and for my future.
We want to thank the SEAS program, the Center for Space Research, UT Austin, NASA, and especially our incredible mentor, Dr. Judy Reese, for putting this internship together and giving us this experience we've gained over the past 2 weeks. We know it'll impact us for a lifetime. Thank you.
Very interesting. So if you have any questions for Anna, Landry, Brooke, or Sydney, please put them into the Slido app. We would invite you to please turn on your cameras and also your microphones. Our first question for the team is, how do sound waves contribute to the collection of matter in different areas?
Okay, so the baryonic acoustic oscillations, the sound waves in the early universe aren't the sound waves we know today. It's more of like a visualized sense of pressure that goes out. And when the pressure brings certain things together, different forms of matter and atoms, like the stars we see now, start clumping together because it's a dense soup in the early universe. And that dense soup gives off these waves of pressure that we know as sound waves, but you can't hear it because we don't have the same, it's space, a vacuum. So it's sound waves, but the correct term is baryonic acoustic oscillation. So it's those oscillations that'll push these forms and clumps of dense hot matter together to form the stars, planets, and galaxies that we know today.
Great. Our next question is, was it difficult to tell the difference between bad data, galaxy data, and black hole data?
There was absolutely, oh, sorry, Sydney, you go ahead.
I would say that the easiest to see would be the black holes, because they were very clearly horizontal lines across the graphs. Between galaxies and bad data, we got really close on them. We argued about some, but I think altogether it was easy to see with the clear dots. And in the end, for the citizen science survey, they get compared with 15 different decisions, so there isn't as much pressure on getting it exactly correct. It's honestly up to you personally what you see.
What was your knowledge about galaxies prior to this experience at SEAS?
Now, I had taken a few courses similar to this, sort of like data management, but in galaxies themselves, this was an incredible opportunity to see real, actual data and real things in the cosmos. Before we started working, we pretty much had a crash course in Astronomy 3 taught by world-class professors. It was incredible. So yeah, it was an absolute learning curve, but it was great.
And the question is, where did you get the numbers to complete your formulas?
So we got all of our numbers from HETDEX Source Catalog 1. It was one of its released data sets. There was so much data in it. So we specifically looked at things related to redshift, right ascension, and declination. We didn't really perform as much computations because we didn't have the abilities. We were told that it would take a supercomputer to go through all the data we had. So what we focused on was visually identifying, which is indeed the first step in spotting these galaxy clusters, especially at these high redshifts. So we did have a ton of data. We used Excel. We got it from their release data set, but we didn't focus as much on the high intensity computations.
Is astronomy a possible career path for you in the future?
It's absolutely an avenue. I'm mainly focused in the ideas of like data science and data classification. So that's a very multifaceted career choice. So astronomy, looking at this sort of thing, yeah, it's definitely an avenue. Yeah, we'll see how it goes.
What about you, Sydney?
I would like to go into aerospace engineering, and I really think that this has pushed me more into my interest of space and everything that I love about it. So I would definitely consider astronomy as a minor, or maybe even something I can focus on in the future and narrow down my aerospace engineering and sort of like pair it with astronomy. It's definitely so interesting, and I would love to learn more about it in the future.
Great. Well, congratulations to your team. Great research. The Human Exploration Research Analog Team researched current analog missions preparing astronauts for living beyond Earth. The team chose environmental aspects to be monitored, and they defined structures to design an analog mission for full stage mission to Mars. A special thanks to Patrick Petty from NASA Johnson Space Center for his dedication and commitment to the HERA team. Please welcome Team HERA.
Hi, my name is Ilaria Luna. I'm from Washington, D.C., and we are the SEAS Analog Research Group, here to introduce our own analog design called Helix.
Hi, I'm Amol Badrani and I'm from Austin, Texas.
Hi, my name is Raul Garcia and I'm from New York City.
Hi, my name is Andrew Gordon and I'm from Boise, Idaho.
Hi, my name is Eva Herndon and I'm from Los Angeles, California.
Hi, my name is Richard Lin and I'm from Louisville, Kentucky.
Hi, my name is Tyra Level and I'm from Round Rock, Texas.
Hi, I am Ben Major and I'm from Coonersville, North Carolina.
Hi, I'm Hannah Murphy and I'm from Chilton, Wisconsin.
Hi, I'm Jose Zambrano and I'm from Frederick, Maryland.
The analog we created is named Helix, which stands for Human Exploration Long Duration Interplanetary Expedition.
Alright, let's talk about the purpose of Helix. Helix is used to simulate a Mars mission, a transit mission to Mars, residency on Mars, and a transit back to Earth. Now let's talk about some goals we want to achieve in this analog. The first one is resilience of off-nominal events. For example, Cascadian failures, rising temperatures that can cause other issues, actual dangers such as tank explosions. The second is psychological and physiological effects, being isolated in an unknown area for a long time. The third is teamwork capabilities, working with the team to complete tasks. The fourth one is to simulate a self-sufficient environment on Mars, living there while in face of limited resources. And the last one, support robust human robotic and human AI interactions, for example, talking to an AI family.
Since we are doing an analog of complete mission to Mars, we plan on placing our analog on the world's most Mars-like terrain. The climate that most closely resembles Mars is Devon Island, Canada, located in Baffin Bay, which is the world's largest uninhabited island. Devon Island is similar to the habitat of Mars because of the explosive craters, volcanic formations, and the barren and rocky terrains. The surface of Mars consists of craters, volcanoes, and dry lake beds. The remote location of our analog gives crew members the feeling that they are away from people, but in reality they are really just across the water. The location of our analog gives crew members easy access to help if they need it along the mission. The climate of Devon Island varies depending on the time of the year. Devon Island has long winters with temperatures reaching negative 122 degrees Fahrenheit. On the flip side, Devon Island has shorter summers with temperatures averaging only around 41 degrees Fahrenheit, which is similar to the climate of Mars due to the fact that Mars ranges from temperatures of 70 degrees Fahrenheit to negative 225 degrees Fahrenheit. The Helix analog will take place over 365 days, with each day in the analog representing 2 days on Mars. The 7 stages are as follows. Day 1 through 74 will be capsule and transit time to Mars. Day 75 through 217 will be the crew actually living on the Mars base. And then day 218 through 365 will be the capsule and transit back to Earth.
So now we'll be discussing about the crew requirements. We'll be looking for a crew size of 8 members, and for the following qualities: to have passed a Class 2 flight physical examination, to be scuba certified in order to perform EVA tasks, be a U.S. citizen, and to be within 30 and 60 years of age. Mission Control will be looking for any qualities deemed valuable for the analog, such as previous military experience, previous or current STEM careers, involvement in extreme conditions/environments, or team experiences of any fields. Continuing with the crew requirements, we'll be looking for the following for ideal conditions: 1 crew member with a doctorate in medicine, and 1 crew member with 4 or more years of psychiatrist experience. We look for these two qualities in order to prevent any external contact with the analog team inside to replicate an environment most similar to a real space mission. We seek for the other 6 crew members to have a bachelor's degree in any science or engineering field, along with 2 years of experience in their career. Experience could be in military or in science and engineering job. Or we seek for the 6 crew members to have a master's degree or PhD in any science or engineering field.
Here we have the final design for the Helix analog. As you can see, it is made of 3 wings and a trigonal planar pattern. One of these is dedicated to living, one is research, and one is hygiene. You can also see the 2 cube-shaped airlocks on either side of the analog to allow the astronauts to enter and leave the habitat. There is also a capsule for the initial launch and descent from this transit vehicle, and a storage capsule to contain any extra materials that the astronauts may need. There's also a solar panel array to power the habitat, and of course this is the transit vehicle that will carry the astronauts for 72 days twice. This is our first module, the hygiene module. As you can see, it contains 2 toilets and 2 showers. This is due to the large crew size so that everyone can get everything done in a timely manner. We also have a sink connected to a water storage tank. That storage tank is connected to another one farther on in the analog so that we have enough water for the entire journey. You can also see on the far left that we have a waste disposal unit that will get rid of any solid waste, and that solid waste is generated through our water recovery system, similar to the one on the ISS. This will remove any water from waste as well as the air. This is our living module. It first and foremost contains a medical bay for the doctor to work in case any injuries incur. It also includes the exercise equipment, which is crucial for crews to survive healthily in the zero-gravity atmosphere. It also contains the capsule dock, where the astronauts will originally get in and then leave this transit vehicle, and then it contains 8 bunk capsules, each of which is soundproofed for privacy reasons, as we found that was very important to astronauts in our research. And finally, we have our labs and storage module. The storage module, of course, will store all of the resources the astronauts need, and the lab module contains 2 research tables that are empty for the astronauts to use for any purpose they may need, 2 computer stations, which contain a total of 2 desktop computers and 8 laptops, so that the astronauts have as much computing power as they need, as well as a water station and food preparation equipment, including a microwave to allow the astronauts to eat. There are also spaces for larger research devices that may be needed, and of course an airlock connector.
Neutral buoyancy occurs when an object has neither positive nor negative buoyancy. The object will have the tendency to neither float or sink. Neutral buoyancy is created by adding weights to the astronaut. This ultimately simulates microgravity because heavy objects can be manipulated in a neutral buoyant environment. Simulating microgravity will allow the Helix crew to perform EVAs or extravehicular activities. EVAs are significant because it will be necessary, especially during a long-duration mission such as the mission to Mars, that we are able to replace any of the failed hardware components external to the vehicle. The pool will be in an enclosed building, and entry will be through a tube containing a ladder that is connected to the capsule. Infrastructure will be constructed to hold the neutral buoyancy pool. Much like the Neutral Buoyancy Lab, or NBL, the temperature of the water will be regulated at 82 to 88 degrees Fahrenheit so that divers will not be impacted by hypothermia. Additionally, just like the Neutral Buoyancy Lab, the water will be recycled every 19.6 hours. Precautions that need to be taken to ensure the safety of the crew members include having 2 divers per person. These divers will be on standby. Each crew member will also be required to be a certified diver. Layouts to establish neutral buoyancy will take place in the airlock. Additionally, not all crew members will partake in EVAs at the same time. A medical team will also be present in case of any emergencies. In case of decompression sickness, a hyperbaric chamber will be available. Additionally, the airlock will be used as a decompression chamber in order to prevent decompression sickness.
Hi there! Our neutral buoyancy pool will have to be both saline and chlorinated. The salt will make sure our astronauts float, and the chlorine will keep it clean. Because of these highly corrosive conditions, our traveler's stage will have to be extremely resilient. Stainless steel can handle the pool, unlike other metals such as aluminum or carbon steel. A resistant coating should help as well. The windows will use polycarbonate. Polycarbonate is perfectly clear, half the weight of glass, and 250 times stronger. The only drawback is that it scratches relatively easily.
This is our online habitat where the astronauts will simulate living on Mars for 217 days. The habitat is located on Devon Island in Canada. As you can see, the habitat is separated into 3 distinct areas, which are designed to psychologically separate the working and living aspects of astronauts' time. This first area will be the living quarters with 2 floors. The first floor will be open space where the astronauts can have recreational time and public workspace. It will also have an eating space where astronauts can socialize and consume food, along with a kitchen where they can store and prepare food. The second floor will contain 8 bedrooms where the astronauts will be sleeping. The rooms will be soundproof for privacy reasons and keep personal items of the astronauts. The other areas will contain a research and medical zone. The Fab Lab will be a place where things are going to be 3D printed to solve problems. The Human Robotics Lab will be a place for rover and drone controls. The AI Center will be for simulating human interactions with artificial intelligence. The Med Bay will be for the doctor to work in and help mitigate any injuries that may occur. There will be research offices for conducting experiments and working on the planet. Exercise space to keep astronauts healthy in the 30% gravity.
Our solid domes will be made of lavacrete, similar to Trapea. Closed cell insulation will be used in the walls to reduce heat loss and sound. The clear dome will use an aluminum and polycarbonate lattice. Aluminum is lighter than other metals, such as steel or titanium. It also has the advantage of being unable to rust. One bonus is that polycarbonate blocks UV, so no sunburns.
One of our analog's main purposes is to develop methods for the crew's self-sustainability, both in the transit vehicle and on Mars. Most importantly, the crew will experiment with various methods of hydroponic systems, such that they can have different types of food in their diet and fresh plants that will help boost their morale. Once they do arrive on Mars, however, we will be experimenting with different crops that they can grow on simulated Mars soil on Devon Island so that they can test other types of nutritious foods that will help vary their diet. Of course, hydroponics especially requires a large amount of water, so we will be implementing the same water recycling and purification system that is currently in use on the ISS, so that they can recycle up to 98% of the initial quantity of water they will be bringing. Another type of diversification of their diet that we will be implementing is fish eggs, so we will attempt to cryopreserve them throughout their transit time and then thaw them so that they can have some more variety in their diet. And of course, we're going to be using the local resources that we will find on Mars, such as the surface ice, to help supplement their water supply. And lastly, to help limit the amount of pollution and space debris we will be creating, we will try to implement a zero waste policy where we will implement compostable materials so that we don't pollute the planet. And as you can see, we also have other experiments such as planned off-nominals, and we will be monitoring the psychological effects of isolation on our crew, similarly to many other analogs.
With long-term travel to the Martian planet, communications are the largest issue. Radio signals take 5 to 20 minutes to reach from Earth to Mars, depending on the planet's positions. Therefore, Helix will allow for family contact between crew members and their families. But a one-way 20-minute communication delay will be applied whenever there is contact to account for a worst-case scenario in the astronaut's training. Next, human-robotic interactions will be studied. Due to the bandwidth demand required and its limited access, medical and family conferences will be available, but limited. Therefore, Helix will study the use of robotics and virtual reality technology to allow crew members to meet their families asynchronously while maintaining a feeling of physical setting through a virtual reality world. The psychological effects and effectiveness of using virtual reality as a means of family and medical communication will be closely monitored by NASA scientists.
So why Helix? What makes our analog special and different from the others? Well, for starters, Helix encapsulates an entire mission to Mars, starting with the trip to Mars, then the actual stay on the planet, and lastly, the return back to Earth. This differs from other analogs, which may only contain one part or aspect of a whole mission. In addition, the crew will have experience living in both space and Martian environments. The Helix mission will also include a neutral buoyancy lab to simulate Mars and spacewalks, which has never been done before. Helix will provide NASA with the necessary physical and psychological data for future missions to the Red Planet.
Our time at SEAS was truly unique and a life-changing experience that allowed us to forge connections in the aerospace industry and foster a deeper understanding and appreciation for space, science, and engineering. SEAS also expanded our knowledge of the careers truly available to us in the future. These past few weeks have changed all of our lives for the better.
These past few weeks would not have been possible without the help of a few very important people, among which, of course, our mentor, Mr. Petty, who was an invaluable member of our team. Then we have Mr. Stewart, who was so kind as to share his experience as a crew member in multiple analog missions. And of course, Ms. Baggio and Ms. Miller, who were both program managers for SEAS.
Thank you from Team Helix!
Great job, Team Helix. So we have several questions that have been posted to ask your team. We invite you to turn your cameras on and your microphones. Our first question is, what does an analog mission really mean?
So an analog mission is like a simulation of life in space or on an astronomical or planetary body. So, for example, some Mars analogs have been in Arizona or Australia and other places on Earth that resemble Martian terrain. And analogs can range from underwater environments such as the Nemo analog or on land, sometimes in places like Antarctica. And the reasons why they're done is because they're useful for collecting data for long-term missions, both physical and psychological aspects of missions.
How many sites did you review before selecting Devon Island, Canada?
It was around 4 different sites. We looked at all the sites with different Mars-like terrains, but we ended up choosing Devon Island because of that. It was the one most like Mars.
How did your experience at SEAS mirror a participant's experience in an active analog? Andrew, I don't think your microphone is working. Still no. Maybe someone else can take this question and then we'll see if we can get Andrew back online shortly.
Can you repeat it real quick?
Yes. How has your SEAS research changed your ability? How did your experience at SEAS mirror a participant's experience in an active analog? I don't know, Andrew, your microphone is not portraying your voice.
Okay. I think I might just answer.
Okay.
I think one of the most important things was proper teamwork because we could not complete this if we didn't work together.
Great. And how has your C's research changed your ability to imagine what human conditions in exploration scenarios would be like?
So even before starting to design our own analog, we had to research the pre-existing analogs run by NASA or other companies. And so through that, we realized that there were many more variables in terms of space travel and habitation that we had not really thought of, such as with the communications delay or finding out ways to deal with family conferences, of course, like the many psychological and physical effects of microgravity. So there were just many different elements that we had to consider and that we learned about and discovered as we were researching. And so thanks to that, we were able to implement those aspects into our own analog and also try to push the limits of the potential of an analog to simulate those same variables.
What sort of human robotic interactions do you think are most relevant to the analog mission?
Could you repeat that question again? Sorry.
What sort of human robotic interactions do you think are most relevant to an analog mission?
Well, I'd say the most important human robot interactions would probably be for communication between mission control and the actual crew members inside the analog. But when in an actual space mission scenario, I'd say, because in the future, an analog could contain computers replicating family members because there'd be far communication delays would take way too long. So we'd say those two would be the most important ones.
How will the analog account for the reduced or missing gravity that would be a real concern in an actual mission?
I'm sorry, like my audio isn't working too well. Could you repeat that?
Sure. How will the analog account for the reduced or missing gravity that would be a real concern in an actual mission? How would you plan during an analog to practice what would really happen in a mission when there is no gravity?
Well, for like the daily routine, we do plan to have similar exercise times, as well as the neutral buoyancy should also somewhat account.
And then the question is, how are you sure that cryopreserved fish eggs, which will then hatch in an unusual gravity, will develop like fish here on Earth?
So we're not actually sure about that. So that's one of the reasons we would look to test that. Although we won't be able to simulate the actual microgravity on Mars, that will only be in the transit portion of our analog. So we're more so going to be looking at the duration and of the feasibility of just cryopreserving the eggs to see if it's then possible for them to survive after an extended period of transit. So we won't actually be looking at the developmental effects of fish.
And how will the analog mimic zero gravity?
So the analog will mimic zero gravity through our neutral buoyancy pool, which is essentially the best way we currently have to mimic zero gravity. The pool mimics the microgravity environment through being neither positively nor negatively buoyant in the water, which simulates the experience that an astronaut would have in microgravity. And this is significant because through this pool, we would be able to better prepare for any of the EVAs or extravehicular activities that we may need to conduct.
Great. And Mr. Stewart wanted to tell the team, congratulations. He's logged in and watching your presentation today. So congratulations to the team. So we are going to be taking about a 20-minute break. We will invite you to watch highlights of student accomplishments during the Earth and Space Science course. A special thanks to Teresa Howard and Asha Carmacher for scoring and preparing those highlights for us. So we will come back about, let me look here, 2:40.
This year's NASA TechRise Student Challenge has arrived, and this year's flight vehicle is the High Altitude Balloon. 6th to 12th grade teams affiliated with a U.S. school can submit an experiment idea designed to fit in one of these and be tested on one of these. 60 winning teams will be selected to turn their experiment idea into a reality. The winners will have $1,500 and approximately 4 months to build their experiment. You'll get a cool box to build it in and technical support from our awesome team of future engineers advisors. And last but not least, the final experiments will be launched to the stratosphere on a NASA-sponsored test flight. Are you ready to build with NASA? You'll learn a lot and get hands-on with an awesome project this school year. We encourage teams of all skill levels to submit your experiment ideas and join this year's NASA TechRise Student Challenge. Go to futureengineers.org/NASA TechRise to learn more.
Welcome back to the NASA SEAS 2023 Science Symposium. The Texas Atmospheric and Space Research, or TASR team, focused on remote sensing and the contributions to atmospheric and space research. The TASR team's design and research culminated in the launch of their own atmospheric remote sensing devices. A special thanks to their project mentors, Melissa Poore, Bob Twiggs, and Nick Pugh. Please welcome the TASR team.
Good afternoon, everyone, and welcome to the Texas Atmospheric and Space Research presentation. During these 2 fantastic weeks, we collaborated with our mentors, Professor Nick Pugh and Bob Twiggs, Laura Tomlin, and Melissa Poore, to launch high-altitude balloons that aid in the understanding of both the Earth's atmosphere and space. We're very excited to share our findings, so without further ado, let's get started. During this time, I worked alongside many talented individuals to design and launch our high-altitude balloon. It gives me great pleasure to introduce the TASR team, pictured with Dan Tenney, a NASA astronaut. From left to right, on the top row, we have Leah Franklin, Tammy Zhang, Viviano Novello, Robert Twiggs, Dan Tenney, Nick Pugh, Giuliana Trevino, and Ariel Reyna. On the bottom row, left to right, we have Melissa Poore, Haley Gooden, Marissa Tucker, Victoria Mascaro, me, London Franklin, and Janelle Perez.
What is high-altitude ballooning and why is it important? Well, scientists have been exploring the Earth's surface since the beginning of time, and now space exploration is becoming more advanced and common. However, the one area that often gets left out of the loop is the Earth's atmosphere, which is the layer of gas between Earth and space. And high-altitude balloons, HABs, are perfect for studying this. They can reach anywhere from 60 to 100,000 feet above the initial launch altitude, which is right around the Earth's stratosphere. This means they are reaching much higher altitudes than the average airplane. To collect data, the balloons are equipped with a payload containing a variety of sensors to measure pressure, temperature, humidity, altitude, CO2, and O2 concentration, among other things. And sometimes they are also equipped with a camera. It also has a GPS that allows us to retrieve the payload once the data is collected. All of the data collected by the balloon can then be analyzed, made into correlation graphs, and compared with other balloon flight data to better understand our Earth's atmosphere. On top of all that, high-altitude balloons are relatively cheap at around $100 each, which costs a fraction of the amount it takes to launch a satellite into space. High-altitude balloons are extremely accessible and versatile, making these balloons the most efficient way to study the Earth's atmosphere and everything about it. Now we're going to share a little bit more about the TASR team.
Hi again, my name is London, and I was the mission manager at the launch site. I communicated with our communication leader of events occurring at the launch site, and I gave clearance for the balloon to be launched.
Hi, I'm Haley, and I was the materials and data recorder for the launch site team. I made sure that all the necessary materials were accounted for and at the right location. I also recorded vital information, such as timestamps of the balloon launch and cut commands.
Hi, my name is Ariel Reyna, and I was the launch operator for our team. So my job was to protect the balloon from any hazards that would pop it and ruin our experiment. And another part of my job was to conclude the optimal time and conditions to launch the balloon without any problems.
Next, we have the Chase team. My name is Leah Franklin. I was a mission manager for the entire Chase team. I communicated with the communication leader of events occurring within the Chase vehicle, and I oversaw the antenna operations.
Hello, my name is Marissa Tucker, and I was safety and procedures. I ensured everyone was safe and following all rules, and I determined whether an area was safe for retrieving the balloon.
So my name is Janelli Perez. I was the antenna operator, and what I did was pinpoint the location of predicted payload landing and observe the data being received by balloon to aid in finding it.
Hi, my name is Tammy Zhang, and I was the weather monitor and antenna operator for the chase team. As the weather monitor, it was my job to check wind patterns, which helped determine the balloon's flight path, and also check the UV index to make sure that it was actually safe to fly our balloon that day. Also, as the antenna operator, I used the antenna to receive data from the payload.
Lastly, we had ground control team. Starting off with me, my name is Juliana, and I was part of the communications. I created a reliable form of communication between groups and made sure important information was passed between the groups.
Hi, my name is Viviana, and I worked in data analyzation for the project. The main part of my job was to analyze the data collected from the payload, such as the coordinates, altitude, temperature, and humidity. For the coordinates, I would chart the location on a map in order to visualize the path the balloon took. As for the other data points, I would graph the information on Google Sheets and Excel in order to present the findings accurately. Afterwards, I would share the created items with the rest of the team in order to explain it equally.
Hello, my name is Victoria Mascoro, and I was the data collector for our ground control team. Now, I specifically was able to read and analyze all the data that was being transmitted from our payload, specifically the latitude and longitude that was then I related to the data analyzer. And then I was able to inform and communicate many of the major problems that were coming with our programming. So I made sure to take a heads up as well as stop anything that may have been tracked when following the balloon.
In preparation for our launch, we used a balloon, payload, helium, and other materials to construct and measure the high-altitude balloon. In addition, we used scientific weights and a weighing instrument to find the balloon's neutral buoyancy point and ensure that the balloon can support the weight of the payload. The launch team used communication devices to communicate with the other teams and a journal to note the time of launch, the initial direction of the balloon, and other important events and information. The operations team used laptops to predict the flight path of the balloon and track the live coordinates received from a high-altitude balloon. They then transferred this information to the chase team through communication devices. The chase team used antennas and communication devices to receive information about the location of the payload.
Following our materials, this is our most important material. We have our payload. Our payload is a motherboard, and it consists of two sensors, one that senses pressure, temperature, and humidity. As you'll see, it connects to the red wire. Then we have the second sensor, which at the bottom connected to the black wire. It senses carbon dioxide, hydrogen, methane, and other volatile gases in the atmosphere. Next to that, we have the blue component you see on the board is our GPS antenna, GPS electronics, and then the yellow and white component you see on the board is our GPS antenna. Then to the left, beneath our GPS electronics, we have our radio antenna, which is the red component you see. And connected to that, we have the radio antenna jack, which, senses everything. It's the main antenna. Next to that, we have the Chow ZPU. And then we have our battery underneath the board to power it all.
One of the best factors of learning new things is being able to share with others. Here on this collaboration page, we have our team sharing with the Eclipse team about our new findings. And here we have pictures of us on roller coasters and Six Flags, demonstrating altitude and humidity on a ZQ, as well as a tethered launch and sharing our experiences with it.
Important aspects that we discussed with other groups were the procedures. First, we measured out the payload and added around 30 grams for a positive lift. Next, we measured out the length of string for how high we wanted our balloon to go. Then we filled our balloon with helium with around 32 inches in the balloon's diameter. Then we used lab weights in a Ziploc bag clipped onto the balloon's string to measure the balloon's weight. Then, once the balloon was neutrally buoyant and not going up or down, and weighed at least 100 or more grams than the payload's net weight, we connected the payload to the balloon.
On the payload and test it to make sure that it is sending the correct data. To do this, you can check the time given on the payload with the real time that you have from a clock or a phone to make sure that the data is synced up. Next, you have to raise the balloon up to your preferred height and hold it in place for about 60 seconds so that it can collect the data. So after you record and collect the data during your flight, after you finish, you bring the balloon back down and turn off the payload. Untethered launch, measure out around 3 feet of string to hold the payload and create a message in case it goes missing. So this would contain your contact information and your name and what your project is about. And ensure the GPS system is functioning properly and consistently, and predict its flight using a website so that you can find it, and proceed with the rest of these steps.
Following the tethered procedure launch, what is a tethered launch and why did we do it? This tethered launch was a balloon with a rope attached that gave us easy retrieval, and it had an SD card inside for data, and no GPS was necessary. Why did we do this? It was an opportunity to teach others and give us experience for our future launches.
Our Trial 1 free launch was on July 12, 2023 at 15:09, where the temperature was 103 degrees Fahrenheit with a 9-mile-per-hour wind heading north. The payload weight was 180 grams, and the neutral buoyancy weight of the balloon was 195.5 grams. 22 minutes after the initial launch time of the balloon, the first cut-down command was sent to the payload. However, when there was no confirmation that the cut-down command was received, a second cut-down command was sent at 15:37. Shortly after the cut-down command was sent, the operation team stopped receiving data from the payload. The chase team continued to attempt to locate the payload based on the last received coordinations. Unfortunately, after no success in locating the payload, chase operation was aborted at 16:03.
During this trial, we encountered many unfamiliar situations, which allowed us to be better prepared for our next launch. We were able to redesign our pre-launch plan and develop an essential materials list to have a more efficient launch. We also relocated our ground team location due to a Wi-Fi connection issue. Although we had to redesign many aspects of our launch, we also discovered many things that worked efficiently, like our antennas. This experience allowed us to gain knowledge and experience to improve on our future launches.
For this next slide, I will explain the maps we used for the first free launch trial. On the left, we have the predicted flight path made using stratoflights. I inputted the launch time, altitude, and coordinates to produce this result. This helped us determine the direction the balloon would initially fly in and gave us a general area to send our chase team to. On the right, we have the actual flight path the balloon took. In order to map it, I inputted the latitude and longitude I received from the payload into Google Sheets and used the extension Geocode by Awesome Table to visualize it. We see that for the most part, the actual flight matched the predicted flight as they both flew northeast initially. However, we saw that the balloon continued on in that direction and didn't reach a high enough altitude to turn back as predicted. This might have been because the balloon did not have enough helium. Now we have the charts graphed with the data extracted from the payload. On the left, the graph displays an opposing relationship between temperature and humidity. As the balloon reached higher altitudes, we saw that the temperature would increase and the humidity would decrease. The same relationship can be seen on the graphs on the right. As soon as the balloon launched from the initial 260 meters, data regarding the humidity and temperature in regards to the altitude were collected.
Now we have trial 1 pictures. So on the first, we have the ground team setup as well as the antenna. The antenna was connected to a tripod so that ground team could keep an updated and refreshed system of the balloon to know where exactly it was, and of course to update chase team. With that, the board and the tree of script, specifically the board was found inside of the payload, and it was able to then track the GPS, ethanol, CO2, and H2 emissions, as well as other things. But the tree of script was a more in-depth look at to what it was exactly tracking. So if the GPS was being updated every 20 seconds to about a minute, the ethanol and CO2 would also be updated. And finally, the Bluetooth terminal as well as the ping for it was for chase team's location of it. So they had their own handheld Bluetooth connection to a phone that then would tell them where exactly the balloon was, as well as the other things that ground team was also monitoring. Now continuing on with other trial.
So for the second trial, the payload and balloon was launched at around 2:35, with the payload having a weight of 140.8 grams. After 5 minutes, the launch team lost visual on the balloon, and during the launch, the chase team stopped receiving operation data at 2:47, with the last chase ping being at 3:17. And finally, at 2:45, the cutdown command was sent because of discontinued data. So due to a modification of the code before launch, we were unable to test the connection between the payload and our receiving computer. And this resulted in a system failure during the balloon flight that caused a malfunction in receiving the payload's location. Because the live GPS location was not available, we decided to issue a cutdown command earlier than expected. And no confirmation of cutdown was received, so we were unsuccessful in finding our payload. Despite these difficulties, though, our prior trial experience enabled us to plan well and work as a cohesive team.
Following the previous slide, you can see pictures taken from Trial 2. They encompass different stages of our launching. On the left, you can see how all the teams met up first on the ground to prepare the balloon for launch. Across from it on the right are our ground team when we first realized we weren't receiving coordinates from the balloon. You can get a closer look into the equipment we were using on the bottom left. Across from that are our groups in their respective areas. We have our launch team on their way to the roof and the chase team observing how to position the antenna in the best way to receive pings. Overall, this launch was a great learning experience, so here's what we learned.
We learned that in order to make the most successful project with a lot of people working on it, such as our group of 10, it is imperative to create procedures that everyone must follow before, during, and after the project. It's also always better to have more than one person check on the predictions of our flight so we can get the most accurate results of where the balloon will be landing and make sure the data that was put into the predicted flight simulator was correct. While we were doing our initial research, we understood that breaking up the teams into smaller subsections allows us to be the most organized and have specific people check up on what exactly their teammates are doing and create goals that can be accomplished. Now, my teammate Victoria will tell us the rest.
Continuing on from what we learned, we understood that there were going to be many problems that were going to occur throughout the ballooning experiment, but we understood that we had to work through them and communicate with each other throughout it all to solve them and to understand specifically what the problem was. Now, with that, we were able to make sure that every aspect of the project, including the procedure of it, was clarified before the launch so that not only could it run smoother, we could spend more or less time on things that needed to be fixed, as well as just making sure that everything had someone designated to. So which, as well as with the roles, we were able to break them down a bit more specified, as well as a bit easier and flexible to what everyone needed to do, so that no one could be left out and that everything was clearly stated to make sure that everyone had the opportunity to contribute to the project. Now moving on to what specifically we can apply.
We applied our learning of procedures to how we broke down certain instructions. Because we understood the procedures had to be as clear as possible, we applied what we learned into creating a list of the things we had to do in preparation for the launch. This also helped for the future launches because if something went wrong in a previous landing, we could know which step wasn't taken correctly and fix it for the next one. Because we wanted to maintain validity when it came to possible predictions of the landing, we made sure that we had people check the path or even put in their own in the computer to make sure the results looked right and were similar to one another. We also applied that to other aspects such as our data analysis and comparison of certain data such as temperature versus humidity. Since we understood that our team could divide and conquer with different tasks, we split our entire team up into groups and made a clear list of the objectives that each team had relative to the balloon launch. As we did multiple trials, we continued to utilize the same team objectives for the launch. We also had a communication system for certain individuals to make sure every team is ready and are doing their specified tasks correctly. During the trials and tethered launch of the balloons, we clarified each step that was being done and made sure that every member of each team understood what was going on so everyone had the chance to accomplish their goals effectively. For our balloon launch, the teams were debriefed and were given time to ask questions. This also occurred after the team was analyzing the data results collected from the balloon. The results that we split into were purposeful so everyone could be involved and people would pay attention to specifically their task, which would prevent mishaps from occurring. The role breakdown allows every person to pay attention to the smallest details of their job and be successful in what they do, because if all 10 of us were focusing on one thing for the launch, there could be a possibility of a future failure since we weren't observing other aspects of the project.
These are our references. With that, our presentation is now concluded.
We would like to thank the Center of Space Research, especially Ms. Selena and Ms. Margaret, for their hard work and dedication to this program. We would also like to thank our mentor, Professor Bob Twiggs and Nick Pugh, for their time and expertise, alongside Melissa Port and Laura Tomlin for their dedication to the program and hard work. At this time, we will take any questions or comments.
So I would like to invite the TASR team to please turn on their cameras and unmute their mics. We have several questions that have been posted. After the cut down command, was the rest of the data received?
Okay,
I can
so
take
on the first launch, after the cutdown command was sent, we stopped receiving data from the payload. We believe this is due to it going outside of the GPS location area. And on our second launch, we had a system failure where we didn't receive any data during the launch. So we sent our cutdown command early and we didn't get any data before or after the cutdown command.
What
if I can add on, yes. So if I can add on to the first trial that we did, another issue that we faced with the cutdown command was when we initially commanded it to do the cutdown, the resistor, we believe, heat up too much. As the resistor is supposed to heat up to cut down the wire, we believe that it just reached too high of a temperature, and it may have
caused some of the system to malfunction, and we weren't able to receive data afterwards.
Why does the predicted flight path vary so much instead of going straight?
I can answer this question. So normally we check the wind patterns to determine the flight path, and depending on which way the wind blows and the changes in wind patterns, that's why the flight path varies so much instead of just going in a straight line.
And what challenges did you have testing the Z-Cube prototype?
So with that, it was our second trial that we actually made the Z-Cube be tested. The biggest problem I would say that we did have was that all the data was stored on an SD card. So unfortunately, when we did not receive that balloon, we didn't get any data back. Unlike our first trial where we were receiving data as the balloon was being flown out of the air, the Z-Cube still did not receive any data when we were back. So that is one issue I would say.
What redesign do you think would be needed?
I can take this question. So a lot of the things that we noticed had to do with just, I'm guessing, the temperature of certain things. Talking about the resistor again, we were discussing ways that we can maybe cool some of the materials before launching them, because when we were launching them, the temperatures like outside were around 104 degrees. So we believe that mixed with just raise the height and altitude just was too much heat on top of heat. So if we could find a way to just cool down the materials inside, I believe that would allow us to receive more data.
What results surprised you the most and why?
So with that, I would have to say, first of all, the altitude. When we looked over it on our first trial, it had showed that it was over 1,000 miles up in the air. And as well as when we were on our second trial, it had showed it was over 920 miles. So to put that in perspective, we had launched it very high. We were shooting for 30,000 in the air. And that was probably the most surprising to see that our balloon was able to be filled up and pushed to that limit without popping and still being able to receive data with the high temperatures that were in that area.
And how did the Z-Cube data on the roller coaster compare to the data from your tethered balloon?
I can take this one. On the roller coaster, we were able to get a lot more information compared to the tethered balloon, because the tethered balloon, we're just in one place, like it didn't move very much, while on the roller coaster we tested different roller coasters, their altitude, humidity, and temperature, so it gave us a lot more information.
And if you were given more time, what would be some additional things that you would like to test?
I can take this one. So if we had more time, I think that we'd like to test like the volatile gases in different stages of the atmosphere. We did get some data, but because not all of the balloons launched to the altitude that we expected them to launch at, some of them were varying, a lot of them were varying actually, we weren't able to accurately track those, so we resulted with just taking altitude, temperature, and humidity instead of the volatile gases that we wanted to use for the purpose of just studying climate change.
And then were you familiar with high altitude ballooning prior to joining this project?
Tim and I were familiar with high altitude ballooning, but we didn't know all that we could accomplish with it. Thanks to our mentors, we learned in depth all that could be done, including the tracking of the temperature, humidity, and then even tracking it through a GPS with Arduino.
So did C's happen to change your STEM interests in any way?
So for me, it really did. Right now I'm trying to accomplish my associates in computer science, and some of the things we did in C's was soldering. So when we did like some jiggies, I don't know how to explain it, but my teammates know what I'm talking about. We soldered, and it was really interesting because I had never done it before, and so I think that like made me think about what other things I could do besides, programming.
Great. And now that this project is over, applying what you learned, What would each of you do differently?
I feel like I can start this off differently. I don't think I would change much, but if I had to change something, I think the initial purpose or the initial direction that we were to go in, there was a lot of things when we were first starting the project. There was a lot of things that we were told to look at, to study, because there's so many things that you can do with high altitude ballooning. And just like Juliana had mentioned, we were aware, but we didn't know all the specifics. So I think if we were to start this project again, we would just choose to study one specific data point and go off with that instead of trying to gather all this data at one time.
And how does climate change affect conducting climate science experiments?
I can take this one. So for one of the examples, the climate change really affected us, like how Viv had said it overheat one time on our Arduino, cutting the cutoff command to like malfunction. So that's another, I know during these 2 weeks, Austin was at the highest point it had ever been. And so that was another way the climate affected it.
Great. Well, congratulations on all of your research. You've done a wonderful job, and you were our first all-girl team at SEAS. So congratulations. So the Exoplanet Transit Project was guided by Tom Rutherford, an astronomy adjunct professor at East Tennessee State University and King University. He provided students the opportunity to investigate and understand exoplanets. Our thanks to him for his guidance and commitment to the SEAS interns. Please join me in welcoming the Exoplanet Transit Project.
Hello, we are the Exoplanet Transit team. Unfortunately, our first team member, Sol, is unable to make it, but I'm Caroline Kanoki.
I am Nate Moretsky.
I'm Noah McCormack.
I'm Rama Musker.
I'm Neha Nayak.
And I'm Neil Parachuri.
We also have our corresponding author and mentor throughout this entire process, Tom Rutherford.
To begin, I'm going to start with an interesting fact. According to NASA, it is estimated that there is at least one planet for every star. A bit of background information. What exactly is an exoplanet? An exoplanet is a planet that does not orbit our sun, a planet that is, in other words, beyond our solar system. So what is an exoplanet transit? This video illustrates what an exoplanet transit is. It occurs when an exoplanet passes between its star and an observer. When this happens, the brightness of the exoplanet's star temporarily decreases from an observer's perspective. Also, the mid-transit time of an exoplanet is when the exoplanet is directly in between its observer and its star. So the bottom of the graph. And our two main goals from this project were to detect exoplanets using the transit method and to determine the exoplanet's mid-transit times.
Now, as we calculated most of these properties, there were a few main things that we were measuring. Firstly, there was flux and magnitude. Now, both flux and magnitude measure the brightness of astronomical sources, but they are a bit different. First of all, flux measures the brightness in watts per meter, while magnitude uses 6 magnitudes, with the brightest at 1 and the faintest at 6. A star at magnitude 1 is 100 times brighter than a star at magnitude 6. Along with these measurements comes uncertainty. The software that we use calculates this uncertainty from external forces and creates a margin of error. Lastly, we measure the Julian date. When measuring time, the Julian date system is more efficient because astronomers need to calculate and subtract and add dates, and the Gregorian calendar, which is what we normally use, isn't as efficient. Now, throughout the project, we studied 3 planets. Firstly, we studied WASP-104b. WASP-104b is a gas giant that orbits a G-type star. A G-type star is the 5th brightest star and is usually a yellow or yellow-white color due to its temperature. For example, our sun is an example of a class G star. Now, WASP-104b has a 1.8-day orbit around its star, and it is 0.02918 AU from its star. And 1 AU equals 93 million miles. WASP-104b is also 466.4 light years from Earth, and it was discovered in 2014 on the Kepler-2 mission. Now, the second planet we studied was Qatar 6b. Qatar 6b is also a gas giant exoplanet that orbits a K-type star. A K-type star is the 6th brightest star on the class system. Qatar 6b has a 3.5-day orbit. It is 0.0423 AU from its star. It is 329.4 light years from Earth, and it was discovered in 2017. In 2017, it was discovered using exoplanet transit, which is exactly what we did on this project. Now, lastly, we studied KPS-1b. It is also a gas giant planet, and it also, like Qatar 6b, orbits a K-type star. It has a 1.7-day orbit. It is 0.02269 AU from its star. It is 857 light years from Earth, and it was discovered in 2019, also due to transit, by an amateur astronomer who was using CCD telescope, which is a very affordable and available telescope for most people to use.
So let's talk about a little bit of exoplanet and star naming. So for stars, the naming convention utilized is project-number indicating discovery order. And for exoplanets, the naming convention is host star name, and then a lowercase letter indicating solar system discovery order. And this order is alphabetical, starting at B. So for example, some examples of star names could be WASP-104, Qatar 6, or KPS-1. And exoplanet name examples are WASP-104b, Qatar 6b, and KPS-1b. So here's a more in-depth example of an exoplanet naming convention. On the left-hand side, it indicates that this was found in the WASP wide-angle search for planets. In the middle, it indicates that it's the 104th to be found in the WASP, and B indicates that it's the first exoplanet to be discovered from its host star, WASP-104a. So why do we study exoplanets? There are 3 main reasons. First is to better understand how these systems formed and evolved. The second is to find out if and where life can exist on other planets. And the third is to give us insight into Earth and our own solar system. So here was our procedure for this project. So firstly, images were taken on telescopes. Second, these images were calibrated to reduce imperfections in the data. Third, the images were ran on AstroImageJ, which is an astronomical software. Fourth, this data from images were recorded using spreadsheets. Fifth, we made graphs from this data to indicate or show the transits. And sixth, calculations were made on topics such as mid-transit times.
So the telescopes used were from the Southern Association for Research in Astronomy. The association consists of 15 colleges and universities. And then telescopes are remotely operated. There's several locations from Kitt Peak National Observatory, Cerro Tololo, Roque de los Muchachos, and La Palma. Calibration and exoplanet observation with AstroImageJ. Calibration is changing the magnitude through observations, and it's essential when looking at images. It ensures removal of instrument biases and inconsistencies, leading to more reliable data. AstroImageJ is a powerful software program used for analyzing astronomical images, including exoplanet observations. Key calibration processes include dark frame subtraction, which is eliminating thermal noise and dark current by subtracting dark frames, flat fielding, which is correcting for pixel to pixel sensitivity variations across the image, bias frame correction, which is removing the electronic offset from the camera's detector, hot pixel correction, which is cooling the telescope about 40 degrees less than the surrounding temperatures using liquid nitrogen. Calibration improves the precision and quality of light curves, enabling better detection of exoplanet transits, variations in their brightness. AstroImage J is a user-friendly interface with automated tools making calibration transect generation more accessible to researchers. Accurate calibrations and transect analysis play a vital role in advancing our understanding of exoplanets and their characteristics.
So, AstroImage J is a computer application that allows researchers, students, and alike to conduct experiments and study the universe. The program lets us interact with .fit files, which are like an image, but with interactive properties. They're flexible and allow for interoperable data transfer. AstroImage J is actually an extension of an older ImageJ program, and the original ImageJ program was developed by the National Institute of Health for Biology, but astronomers saw its value and repurposed it for their use. Astro adds astronomy plugins and macros, and it includes tools based on the Godogen ImageJ astronomical resources. So we use AstroImage to process our .fit files for each solar system, basically the star and exoplanet in question. So apertures are placed on both target and comparison star, and then pre-designated magnitude of comparison star is entered, and then the target star magnitude will update, and then the Julian date is recorded, which is basically our x-axis, and then error is also recorded and shown as a scatter graph, and then successful result should have a dip in the middle. This shows that the light reaching from the star is being ever so slightly obscured by the exoplanet passing between.
Yeah, so diving into our actual data, our actual calculation was the mid transit time, which we did by estimating where we can kind of tell is the beginning and the ending point of the transit time, and then using that formula of beginning plus ending over 2, we can find the midpoint, which should hopefully line up with the deepest part of the transit. So now we're going to show you some of our calculations and our light curves. So here are our results. So this is the one from the last slide. This is WASP 104b. And on the mid-transit time that we got in Julian date was 246.0011.7125. This is Qatar 6b. This is its transit graph. As you can see at the very end, it all kind of scatters a little bit. And we think that's because a cloud went over the top of the telescope when it was observing. And its mid-transit time was 246.0073.5825. And this is our final one that we did, which was KPS 1b. This is its transit graph. As you can see, it's a little more shaky than the other ones, but there is still a clear transit there because the dip is still much more than all the air bars on all of our points. And the mid-transit time was 246.0073.5825. And here are references. These are all the sources that we used in our research. And our slideshow template is from slides ago.
Here are some of the highlights from our project. The 4 main highlights we thought were collaborating on graphs and troubleshooting, working with peers and mentors, working in a real-world scenario with scientific images, and learning about software applications such as AstroImage. We'd also like to take a minute to thank everyone on this slide that helped us with this project directly or indirectly in any way.
As mentioned earlier, one of our members on the team couldn't be here today, and his name is Saul, and this is what he had to say about his experiences with the project. And you can pause and read if you would like to.
SEAS has enabled me to work with real astronomical data. This opportunity has solidified my desire to pursue a career in astrophysics. I'm beyond grateful for the work my mentor has put in my experience in SEAS.
As for mine, having been passionate and interested in astronomy for years, the prospect of working as a team on a project with real telescope data sounded incredible. SEAS opened my eyes to how fun and rewarding research in practical astronomy can be, and it has further taught me how to work as a team and effectively collaborate with others.
This NASA SEAS internship was a really unique and educational experience for me. I learned lots about exoplanets and scientific analysis. I'm really grateful to my mentor and peers for our work on this project, and thank you so much for this opportunity.
Getting a chance to work with SEAS, my mentor, and fellow interns with like interests on this project has really helped me grow. I've built teamwork skills, gained some insight as to what it might feel like to work in a real team, and built upon my own knowledge of astronomy. I've always wanted to be an engineer, and this opportunity showed me a little of what it's like and is setting me up for success in a field that I'm passionate about.
Working on this project was an amazing opportunity where I was able to work with people with like-minded interests and learn from NASA professionals. I especially loved combining my love of computers and astronomy and seeing how technology plays a huge role at NASA. It was a great experience, and I hope to pursue something similar to this in the future.
Now, personally for me, engineering has always been the clear choice for my future, but it was difficult to find opportunities in real world scenarios where I could understand what engineers do day to day. And the SEAS internship program gave me a chance to actually work in astronomical engineering and see a part of what they do day to day. And I also got to see a part of my future. And I'm sure I speak for everyone when I say thank you for this opportunity.
So we have several questions for the Exoplanet team. We invite them to please turn on their cameras and microphones. Our first question is, how did you select which exoplanets you would study?
Before we answer our question, we have an amendment to our video. So the mid-transit time on our last exoplanet was actually 2460103.696. So
thank you.
As for how we picked the planets, we were given the data by our mentor, so we just did the data that he already had available.
And what is something that you feel like you gained from this internship?
I'll take this one. I got a chance to work with a team that we're all passionate about at least somewhat similar things. And it really built upon my knowledge that I had previously had, and it gave me the chance to move forward with my career.
What difficulties did you encounter working as a virtual team?
I can take this one. I think honestly, like scheduling was really interesting. Like to kind of combat that, because like being a virtual team, we had people like spread all across the country. So I think just like working with that, and then of course like collaborating and learning, because like none of us knew what we were doing really before this. So just trying to do that was really, really interesting, and definitely set me up really, really well for work after SEAS.
So did anyone have a background in astronomy or had worked or thought about a career in astronomy prior to SEAS?
I can take this one. I did think about a career in astronomy, but I didn't know much about the field. So this program definitely helped me learn a little bit more about what it could be like to work in the field.
Great. And what are your thoughts on possibly finding an Earth 2?
I can take this one. I think it's very interesting, the idea surrounding finding an Earth 2, although I guess the possibility of us actually being to live there would be very low, since anything that we could find would probably be very, very far away and take years and years and years and years to get there.
I think adding on to that too, if I could really quickly, The current news, well, current-ish, of James Webb finding like water vapor on a rocky exoplanet. I think that really goes to show how like the search for Earth too, even though like Caroline said, we might not actually be living there, but just like getting that rolling is like really fascinating, and I'm really excited to see where that goes.
Great. Well, you've done a wonderful job with your research, and I want to thank each of you. So the Earth System Explorers virtual internship engages interns with NASA satellite products, as well as digital tools that scientists use to monitor and document our changing landscape and climate. This year, teams focused on land cover change and the public health threat of mosquito vector-borne disease. We are fortunate to have the expertise of several scientists and educators as mentors in this outstanding group of students. Our thanks to Dr. Rusty Lowe, Cassie Sofing, Andrew Clark, Petter Nelson, and Dr. Erica Podest as mentors for the Earth System Explorers group. So we will have several presentations followed by questions for 3 or 4 groups. So please, as each group is talking, post your questions in the Slido app, and we will ask that after the first group of presentations. Please welcome the AI model classification team.
If you watched the C's required intern videos, you have an idea of why land cover data is so important. Land cover data is extremely important because it helps us look at the world clearly. Using land cover data, we can assess and predict changes in our natural environment. We can use it as a climate change metric, a drought predictor. Its components can be applied almost everywhere. Mosquitoes, for instance, land cover data, through that we can look at changes where changes in their population might happen, such as during droughts and during floods. And we can also predict what species of mosquitoes those mosquitoes could be based on the land cover data. The problem with land cover data is it's not a super detailed picture. If you pull up the Sentinel-2 images, they're beautiful and they are complex, but because it takes so much time to go through said images, they are basically dumbed down into squares of urban and forests, and they're really undetailed. AI could help us improve land cover monitoring because it'd be faster, it would be cheaper, and it would require less manpower. It would be much more efficient. And because of that, we could assess and see minute changes that are happening on the face of the Earth.
So to start off our research, we defined areas of interest within each of our local communities. So each area of interest covered a 100 meter by 100 meter area and contained 37 individual points. Individually, we used the Globe Observer app to collect photographs and analyze the land cover of each of these area points. We then uploaded our grid to Collect Earth Online, where we individually analyzed satellite images of the same areas. We use this data as our human classification section that we would eventually compare with the AI algorithms. And then using the AI model, we then determined how an AI would classify the same areas that we did in order to spot discrepancies between the two methods. We utilized the platform Pearl, which was developed by Microsoft to inference land cover data across the United States. And then after that, we calculated the frequency of each land cover classification per AOI versus the AI model's general percentages. Then we outlined the categories in which the misclassifications were the most common in the AI classifications. From that, we found that the tree cover and grass cover areas were the categories with the most AI error, and we also found that the average difference between the human classified AOIs and the Pearl model classified AOIs was around 5.5%.
Going into this project, we thought that the AI classification abilities would match or surpass the human classification abilities. However, we soon realized that there is no correct answer for land cover classification. So we compared the AI classification to the human classification. There were some instances where the AI was blatantly incorrect, however. For example, in one of our example images, the AI classified standing water as impervious surface or roads. In the future, we could remedy this by training the AI with more data from different areas and at different times to account for lighting and reflections from the sun. For example, a reason we would need to classify this in different regions is because vegetation may be misclassified due to different regions having different types of vegetation, and some may be classified as trees when they are, in fact, are not trees.
And then we have a few thank yous. We have one to Selena Miller, who was really integral in helping organize the SEAS program. We also have a big thank you to our Earth Systems Explorers mentors, Dr. Vestan Lowe, Miss Cassie Sofing, Mr. Peter Nelson, Dr. Erica Podest, Andrew Clark, and our peer mentor, Marvel Hanna. Thank you.
So I remind you to please put your questions for this team in the Slido app. Our next presentation is about utilizing convolutional neural networks to identify the environment where each mosquito genera thrives.
My name is Fatia.
My name is Johnny.
And my name is Barack. Today we will be talking about our research project titled Aedes, Anopheles, and Culex, utilizing convolutional neural networks to identify the environment where each mosquito genera thrives.
Although mosquitoes are an important asset to the food chain because as larvae they serve as food for fish, and as adults, flies, they serve as food for birds, bats, and frogs. Mosquito bites can transmit deadly vector-borne diseases and viruses to human and livestock, killing an estimated 700,000 humans per year, according to the U.S. Centers for Disease Control and Prevention. And an interesting fact is that according to Virginia Commonwealth University, due to urbanization, some mosquito species become anthropophilic. They prey specifically on humans, and accordingly, the virus prefers humans over animals as their host. Urbanization often promotes mosquito population growth, thereby promoting virus population growth.
A way that we choose to analyze this issue is to identify what types of mosquitoes threaten the different communities, as each of the three major mosquito genera, Aedes, Anopheles, and Culex, transmit different diseases. Aedes transmit dengue and Zika. Anopheles transmit malaria, and Culex transmit West Nile virus. This research utilizes Mosquito Habitat Mapper, MHM, observations from the NASA-funded Globe Observer mobile application, made by citizen scientists around the globe to determine which genera of mosquito is most prevalent in rural, suburban, and urban communities in each region.
Each of the 13,000 observations of mosquito habitat and mosquito larvae we analyzed were used in the AI model Convolutional Neural Networks, CNN, that came out with an 85% accuracy to classify the habitat as either rural, suburban, or urban, and the corresponding mosquito larvae as Aedes, Anopheles, or Culex, to then calculate the similarities between the type of community the habitat was found in and the corresponding mosquito genera. In order to identify what mosquito genera was most prevalent in each type of community within each region?
We are doing this research because if there's a major correlation between mosquito genera and community type, then that means that different communities require different treatments for the vector-borne diseases transmitted by mosquito genera. Depending on the mosquitoes that threaten their area, and having that knowledge can save lives. This research is only the beginning to a much more thorough examination of the factors that keep mosquitoes as the most dangerous creature to humans in the world.
We'd like to thank all of our SEAS coordinators, including Cassie, Dr. Rosillo, and Peter Nelson, and our peer mentor, AJ Caesar, for guiding us through our project and supplying us with all their knowledge and expertise. A highlight of the internship was meeting all the amazing individuals and learning new things from them every single week. But a challenge was the AOI fieldwork, specifically going to each of the points and recording the data and observations, but it was all worth it in the end.
My NASA Earth Science internship has been an incredibly transformative experience that has profoundly shaped my future education and career plans. Working alongside top-notch scientists and researchers at NASA has opened my eyes to the profound impact of Earth science on our planet's well-being and sustainability.
My NASA Earth Science internship has been an eye-opening experience that has significantly influenced my future education and career plans. Being part of a team dedicated to studying our planet has given me a profound appreciation for the importance of environmental research and climate studies.
SEAS has helped me further my future education by allowing me the opportunity to meet with many esteemed people in the STEM field.
Our next presentation from the Earth System Explorers team is researching automatic AOI.
Hi, I'm Yuvraj.
I'm Ryan.
I'm Jeff.
I'm Abdul.
I'm Grace.
And I'm Benjamin.
Today we'd like to introduce you to Enhancing Citizen Science and Accessibility with an Automatic AOI web app. We'd like to begin with introducing what is AOI. AOI stands for Area of Interest. It is a standardized data set that can create a high-resolution model of an area, set of coordinates that map an area, and citizen scientists use this app to record observations.
So we, as Earth Science Explorers, have found some issues with Globe. First off, that AOI can only be found externally, and that makes it very hard to navigate as people who are not necessarily very experienced with computer science and earth science. So in order to understand the limitations of the Globe Observer, we surveyed all of the Earth Science Explorer interns and asked them 2 questions regarding their Globe experience. How convenient was the AOI creation process, and how likely were they to repeat the process? We found that many of the interns found that the process was very inconvenient and that they would not repeat the process outside the internship.
It's pretty clear that Globe and AOI creation can be difficult for citizen scientists and SEAS interns alike. So to address this issue and enhance overall experience for future SEAS interns, we aim to develop an app focused on streamlining the AOI process. We hope to answer this research questions. Does the app function in creating an AOI both effectively and optimize citizen science users' comfortability? And if it does it hold up to the current system we have in place?
So some of the potential benefits of a project like this is that it could impact over 10,000 citizen scientists that would use the Globe Observer app in the future. It could significantly bolster retention among volunteers because they'd be more motivated to help out if they see more researchers available and they see that it's easier to get access. And it could also increase land cover accessibility to more people. So our research plan has 4 steps. 1, identify specific features that can optimize user experience. 2, develop those features in a preliminary web app. 3, compare the app with current systems using volunteers. And 4, consider and modify features as needed until we get to our final product. Welcome to our app demo, which was built using ASP.NET Core, hosts a PostgreSQL database, and uses TypeScript for interoperability. Now, after getting to the login page, the user can go to the register page to enter their details. Here, just enter your name. This allows you to log back in after you log out to see your saved data. Now I'm back to the login page. I'll enter my details.
Now, I'll be greeted by a big map and a side dashboard. You'll see your current location as an icon. You can long press on a point. This will be your center of your grid now. And you can create grid. This will give you a quick confirmation and you can create the grid. On the left side, you'll notice that your points pop up with the number, with the positions. This allows you to track your data collection, and the pins pop up on the map. Now, if a pin is in an undesirable location, for example, this is in water, I could slightly move it over to an accessible location, and this is just for better organization. It's not really significant. If I'm in a location and I want to go to the end nearest points, I don't know which are the closest, I could do this. I could say I want to go to the 3 nearest points, for example, and it would give me a quick route. After I'm done collecting a point, for example, let's say I collect this point, right? So I can scroll down to 16 and I can check it off. And now this will take you to the bottom, to the collected area. Pending will decrease by 1, etc., and the pin will turn green. So when the whole grid turns green, that means you're done collecting. Thank you for watching our demo.
So now that we've seen that demo, it's important to compare our system with the previous system. So we did that by contacting 20 volunteers across the continental US, and we instructed them to one group to use the old AOI system and one group to use our system. Then we instructed them to visit all the coordinates on the AOI and do mock observations and time each step of that process, and then swap to either our system or the old AOI system, and then have them do a post-survey review. So we found that the AOI creation process, our new web app was significantly faster than the old system. And we found that the data collection process was significantly faster as well because of the grid.
Okay, so future steps, we're hoping to build a mobile app to incorporate more features, customize the AOI grid to 3km by 3km, and create multiple AOIs from the user account, and more organic tasks between points for navigation. In conclusion, we learned how to make an AOI 37 points more accessible, change the ability of more data for NASA landscapes, and create a new app for ideas to fix the AOI grid, and change the effects of the inaccessibility of the AOI grid. We would like to thank Rusty, Lo, Peter Nelson, Cassie Sofing, and AJ, Caesar, and Andrew Clark for their help on the project. Thank you so much for watching.
Great work. So our next team will be highlighting the case study of Hurricane Harvey.
Hello, my name is Manila Marie, and I'm joined by Alison Duran, Angie Garson, and Capri Crespo. We're the C 2023 Time Travelers Group 3 of the Earth Systems Explorers, and we're going to be doing a case study of Hurricane Harvey from 2017. We're going to see how cloud coverage can help us see the causes and effects of these hurricanes. So first heading into our project, we first wanted to provide a research paper that we could eventually get published, but also a deep insight into a very interesting topic and get this idea going to the AGU Science Conference. So about Hurricane Harvey, first, it was a really destructive hurricane in recent U.S. history that landed on the Texas coast in the August of 2017, and cloud coverage was a very important factor into this since it can provide a lot of valuable information to the development and formation of these storms. So about our process, we first analyzed hurricanes as a whole, and then we went on to El Nino and La Nina and climate change, since they all played a very important role into this hurricane. And then we saw hurricanes had patterns with clouds and in regards to the characteristics and effects.
Hello, my name is Alison Duran-Uriela, and I'm part of the Time Travelers Hurricane Team. The effects of climate change on Hurricane Harvey. Climatologists agree that global warming contributed to Harvey's impact. Studies have found that the amount of rainfall was 38% higher because of global warming. There are 3 main reasons for this. First being the Gulf region air temperatures were 2 to 3 degrees hotter in Fahrenheit in the past years, which allowed for the air to hold more moisture. Second being the rising sea levels made flooding more likely near Gulf Coast cities. The sea levels around Houston were 6 inches higher than 20 years ago, particularly due to warmer temperatures, melting ice caps in Antarctica. Third, global warming stalled weather patterns in the region that allowed Harvey to hover over Houston instead of moving back out into the ocean. The convergence of all 3 effects allowed Harvey to drop feet of rain instead of inches.
Hello, my name is Angie Carson. Today we'll be talking about El Nino and La Nina. As you can see in the bottom right hand corner, I added that picture showing that how they're both different. El Nino brings colder and wetter environments, while La Nina brings drier and warmer temperatures. Now, La Nina affected Hurricane Harvey because during Hurricane Harvey, it entered the Gulf of Mexico and we were experiencing La Nina, and it actually grew bigger and stronger because of those warm waters. Not only does La Nina bring warmer waters, but it also brings pretty distinctive rain clouds. So during La Nina, more hurricanes and storms form because of those warm waters. So most clouds go off in the ocean and create those storms, leaving us looking up in the sky from the ground, not seeing as much cloud coverage because they're off in the ocean. So we can use satellite imagery comparing cloud coverage between La Nina and before a hurricane or a storm. And if we can see that the cloud coverage is somewhat similar, it shows that it will be a bigger storm and hurricane than we would be expecting. And comparing to El Nino has bigger, white, fluffier clouds. So if we see that before a storm, it shows us that it won't be as big of a storm that we should be expecting. Now that's what we can use La Nina's cloud coverage to compare how big of a storm we should be expecting. Thank you.
Based on what we just learned, we can see that La Nina actually causes colder clouds because the warm air that it brings to the south rises quicker. This rising air causes the clouds to become extremely condensed and become also extremely cold due to the higher elevations they experience. Also, hurricane clouds tend to be colder, so this does correlate pretty well. After the hurricane passes, the sun shines and the clouds eventually dissipate due to a sudden increase in temperature. Also, low wind shear causes more damage since it allows the clouds to stay together more and keep their structure and strength while the hurricane passes. As you can see here in this graph, Hurricane Harvey actually experienced the greatest maximum wind speed right here before it entered, and then it caused the most damage here, which is actually where it had the lowest wind speed. El Nino also brings in thicker, more condensed clouds due to pre-existing cold temperatures. We can see here that El Nino, 1 year before and 2 years after, we can see that those are pretty thick, condensed clouds already. And also here in this graph from our Globe Observer app, that's also pretty condensed clouds right there. Texas is actually expected to get a hurricane this year or next year. As we can see, the clouds look similar to the ones we see from the satellite image right before Hurricane Harvey and also after. Thicker clouds from El Nino mixed with the warmer, newer air from La Nina is a perfect recipe for disaster.
In conclusion, overall cloud coverage observations obtained through satellite imagery and ground-based instruments offer valuable insights into the dynamics and behavior of hurricanes. Integrating cloud data with other meteorological variables enables forecasters to improve hurricane track predictions, intensity forecasts, and warnings, ultimately helping to mitigate potential impacts on affected areas. We would like to acknowledge and thank the SEA's Earth System Explorer mentors, Dr. Rasain Lowe, Ms. Cassie Soafing, Mr. Peter Nelson, Dr. Erica Podas, Andrew Clark, and Yashari Patil, and all of the NASA SEA speakers.
So we have several questions in the Slido app for the 4 teams that have presented. If you would please turn your cameras on and your microphones. The first question is for team number 1. What complications did you run into with land cover data or classifying the images?
So one of the main issues with the land cover data that we classified on Collect Earth Online, it was a very tedious process. And so it took an extreme amount of time. It wasn't extreme, but it was very time consuming for how much work we did. And then the other issue that we ran into was the Collect Earth Online. You can't assume that the human classification is going to be 100% perfect because there is human error. And so there is no perfect baseline of what exactly this land cover is, because as you zoom in, things become more complicated. Just as you look in, depending on like how big your area is. So there's no 100% correct model of land cover that we had to go off of. So we had to compare AI versus human, and neither was perfectly correct.
And the next question is also for team number 1. Was there a particular reason for selecting the AI you used? Why was it selected over other platforms or models?
The AOI we used, it was pretty much the most accessible one. I selected this AOI because it created the most detailed map, or this AI, it had the most detail when we were going through and classifying, which lended better to compare to the classification because the human classification was also super detailed.
So Annika, had you studied mosquitoes or land cover images previous to SEAS?
Actually, no, I had no kind of experience in this kind of field before I tried SEAS. This internship actually opened my eyes a lot to like different possibilities within the NASA field. I never thought like mosquitoes could reveal so much about like the planet and climate and stuff like that. So it was really interesting studying like mosquito patterns and land cover and how they played into everything.
Great. Okay, we have several questions for team number 2. Did you encounter any difficulties working as a virtual team?
Yeah, I think a lot of our issues stemmed from scheduling because of the time difference. Some of us are on the West Coast and some of us on the East Coast. It was hard to really get on the same page about timing and scheduling.
Is there any potential way you can think of way you think a percentage greater than 85% could be achieved?
Possibly if the data sets that we worked with had more information, but considering the data sets we used, I think it'd be very difficult.
And also for team number 2, why do you think the certain species of mosquitoes gather in rural areas?
Because there's less humans cutting down trees and destroying the environment, that allows for more mosquitoes to thrive in those areas and truly populate.
And then we have several questions for team number 3. Did this project, make you have any interest in creating an app?
Yeah, definitely. With the data collection process, we did it early on with the Globe Observer app. We saw that there's a lot of things that a lot of features that we would have liked to be added. So that's why we decided to build this app for future SEAS interns.
Is there a location where others could download and test the app that you created?
As of now, I ran it locally for the test, but in the future, if I'm able to, after I stay in contact with SEAS, I'll definitely try to upload it in the future.
Perfect. And also for team number 3, did you plan some challenges? What are some challenges you had creating this new app?
There's a lot, especially with basically our app works with a different programming language in the back end, and a different programming language for the front end, the map you see. One, integrating Google Maps API was difficult, especially with that big map you saw on screen, and getting those pin overlays was a little difficult. We did plan to have some like a feature that would adjust the pins if they were on water, but for now we had to have the drag functionality, but we were initially trying to use some sort of API that would allow us to like see if the pin's currently on water and move it accordingly. But that required an excessive number of API calls, and that's something we didn't have at the moment.
Great. And questions for team number 4. What is something interesting that you learned about hurricanes that you did not know previously?
So there are a lot of things we learned while doing this project. Obviously, Hurricane Harvey was like devastating, and I live in Texas. So I learned basically that hurricanes go through many sorts of patterns in their development, and that for them to cause the most damage, they actually have to go at a low wind speed, even though on the ground it may seem like they're going really quick and like they're just causing damage rapidly. But it really is when they're at a low wind speed that they cause the most damage to cities and environments.
And has anyone in your group experienced a hurricane in their area? And if you have, did that help you with your research?
Me and Angie both live in Houston, Texas, so we both experienced Hurricane Harvey firsthand. My neighborhood got flooded really badly, and a lot of buildings were destroyed. So it helped just kind of like, I guess, seeing there from a first-person point of view when we were on the ground, and then it was also cool looking back at it from satellite images and seeing how it looks like from above.
Mm-hmm. And Angie, as your team, what made you want to do research about the specifics of one event?
Like Manuel said, we experienced this hurricane, so we both just wanted to gain more research and knowledge over Hurricane Harvey and how it came to be and how it had a really big impact to not only Houston, but Texas in general.
And did you have an interest in studying the Earth and the Earth systems prior to SEAS?
Yes, I did. I was really interested in becoming a meteorologist when I was really younger, so I found a big interest in studying hurricanes.
Great. Well, thank you to all of the teams for presenting. We appreciate the amount of research and effort that went into your studies. So our next group of presentations will start with analyzing the correlation between terrain and the characteristics of wildfires.
Hi, my name is Daphne Rodriguez. I'm here with my team, Trisha Goruso, Renee Sterbrook, and Kate Biddle, and we analyzed the correlation between terrain and the characteristics of wildfires. Our goal is to find the correlation between terrain and the characteristics of wildfires to aid in the development of further fire prevention methods. Wildfires risk to both wildlife and humans, while also causing significant harm to the ecosystem and natural homes of various species. In particular, California has been identified as one of the most susceptible states in the United States when it comes to wildfires. The unique topography of California, characterized by varying elevations, canyons, and slopes, plays a crucial role in influencing fire behavior and propagation. This makes it an excellent focus for the study of wildfire behavior.
Our group first identified the specific data sets we want to collect to analyze our results. We first want to get the average slope and average elevation measurements from the Google Earth Engine in order to characterize the terrain. We also use the UCGS Earth Explorer in order to get coordinate points for each of our wildfires in order to use the Google Earth Engine. We then want to remove any confounding variables by getting wind speed and temperature measurements as measured from the NOAA datasets. We then used the LCMS Data Explorer to get surface reflected data characterized by the normalized burn ratio, and we got area measurements from our CAL FIRE database. We also wanted to measure the change in land cover by using ArcGIS to overlay all of the Globe Observer land cover observations over California to pick out specific observations to characterize each of our wildfires. We chose one Globe Observer observation for before the wildfire occurred and one for after each wildfire occurred in order to measure how the wildfire changed an ecosystem.
Starting with the Dixie Fire, we can first look at photos taken before the fire occurred. Interestingly, in all of these photos, evidence of previous fire damage is visible. After the fire, in the north and east photos, we can see up close the extent of fire damage to the trees. Next is the North Complex Fire. In these photos taken just outside of the fire perimeter, there is no visible fire damage. In the August Complex Fire, on the other hand, there are burned trees visible in the north photo. Moving on to the SCU Complex Fire, the closest globe data came from a nearby location that does not show the burned area, but hints at the terrain present in the burned location. For the Creek Fire, we have globe data at a location directly east of the fire, meaning that in the west-facing photo, the burned area is likely visible in the background. There is no useful nearby data for the Carr Fire, but as Globe Observer continues to be used, measurements could be taken within the fire perimeter that allow for more in-depth analysis of this fire. A summary of this information, as well as our results, can be found on our group's research poster. Through our research, we were able to conclude that the variables which impacted forest fires the most were slope, elevation, vegetation, and wind speeds. As heat rises, the vegetation ignites uphill, which makes the mountainous regions of California much more susceptible to these disasters. And due to the low air humidity, the plant dryness is another factor that increases the spread. Here you see a graph which shows the prime average slope for a fire at around 10 degrees. When examining surface reflectance, we can then see as slope decreases, it then increases, and following the fire, that surface reflectance drastically decreases due to those areas being charred. Specifically, in the Dixie Fire, that value decreases roughly 36%. In conclusion, the wind blows fire into dry vegetation in which the heat rises to the trees above it and therefore causes a massive forest fire such as the ones examined in the previous slides. Thank you very much for listening to our presentation, and we would love to thank our SME mentors and the CSRC staff and our partners, which are listed here. Some of our highlights throughout this internship were hearing from experts and then hearing them provide walkthroughs for their respective research tools, which we used in our collaboration in our small groups and developed a project together. And then we also love presenting this project in this conference here. Personally, the SEAS program introduced new resources and technology to me and helped expand my knowledge of Earth systems. And it made me realize my love for Earth science as well as space science, and I don't need to limit myself to just one category. Thank you very much.
Good job. Our next team focused on uniting deep learning and citizen science for automatic land cover image classification.
Our project is uniting deep learning and citizen science for automatic land cover classification. Meet the team. Before we begin, you'll need to have a basic understanding of Globe Observer. Globe Observer is a citizen science app where volunteers can take 6 directional photos of the land cover in their communities, and afterwards, they'll classify them and upload the images to the Globe database. This is a closer look at the image classification process.
The problem is that making classifications is just too complicated. We sent out a survey to other SEAS interns, and we found that majority of them lacked in confidence in their labeling and believed their labeling to not be accurate. Oftentimes, this led to them not labeling their classifications at all. Other implications are that it's time-consuming, the labeling is inconsistent, and volunteers opt out of labeling their images entirely. All of this leads to an unreliable dataset.
Our solution was to create an automatic labeling feature through a deep learning model taught by citizen scientists. This model was meant to save time, reduce inaccuracy, and aid scientists in future research.
For our research approach, there were 2 main questions we wanted to answer. First of all, could we use volunteers to process large amounts of data in order to train a model? And then, how effective could using a deep learning model be to classify land cover? We used this 5-step process to train a model and analyze a directional photo which would determine whether sky, land, or water were present in an image.
Our data consisted of our SEAS team's land cover observations. In total, we retrieved 5,896 north, south, east, west photos over multiple states and continents. This was done through Python scripts we wrote to organize the data taken from the Globe API and download the photos, and then we downloaded the photos onto a Google Drive folder. This is a snippet of our code here. We classified the images to train using Zooniverse, a citizen science annotation tool. And then we organized our data using an algorithm that filtered out faulty images. Finally, we trained the models using binary classifications that detected whether or not the 3 land cover classes, land, sky, and water, were present in an image.
This is our labeling interface on Zooniverse, where one selects one or more of 3 main land cover categories in the image shown. The tutorial covers possibly confusing pictures such as unclear categories or temporary bodies of water. And these are the statistics from our classification.
So after we gathered our data, we trained a model to learn from this data. So we picked the model based on our desired output, which was the classification of whether a directional photo contains sky, land, or water. So we chose to use a Resonant 18 model finally for its accuracy and efficiency. We trained 3 ResNets with an 80-20% train test split that was stratified, as well as a weighted loss and sampling in hopes of counteracting our severe class imbalance. And then we assessed our 3 models on multiple performance metrics, including accuracy and AUROC. Finally, here are our results. So for our water detection model, we had a high accuracy in AUROC, but a low AUPRC because of class imbalance in the positive class. However, we still had a 0.80 TPR, true positive rate, which suggests that our model is still pretty good at identifying water, even though AUPRC was low. Next, for our sky detection model, we had high metrics all across the board because of our good balance, as well as good weighting and training. For land detection, we had similar issues to our water detection model, with very few images that had no land in them. So because of this reason, we had a pretty low AUROC, but we had a very, very high AUPRC, which favors the positive class. However, we still think this can work well in field because in reality, there aren't a ton of images taken that don't have land.
How effective were the volunteers in labeling our photos? Well, it only took them less than 5 hours to label all 5,896 of our photos, and it wasn't very difficult to set up this universe since it took less than 3 hours, including the time it took to upload the images. And were they accurate? Well, looking at the model performance, they were pretty accurate. And this is some of our future work. Next, we be able to identify all of the land cover categories in the Globe Observer app. Next, we'd like to recreate the model so it can output estimations of how much each feature composes of the area. Lastly, our final goal is to be to build an app and implement it on a mobile platform like a companion app for Globe Observer. These are our references. These are our acknowledgements. And these are some extra resources that you can access by scanning this QR code.
So our special thanks to the 3 teams that just presented. We do have questions for each team, so I invite you to please open. Wait a minute. I think I have one more presentation. Sorry. So we do have another presentation, and this team will be analyzing the effect of urbanization on mosquito population dynamics using the Globe Observer data.
Hi everyone, today my team and I will be presenting our project for the Earth Systems Explorers team. In this presentation, we are going to examine how mosquito population dynamics are affected by urbanization. For some background, insect vectors like Aedes aegypti, Culex, and Anopheles genera spread diseases throughout the United States, such as dengue, West Nile virus, and Zika. With changes in the environment, mosquito behavior has changed significantly in the last few decades. Urbanization is a big factor in modifications made to the environment in which mosquitoes inhabit, prompting the question if urbanization actually impacts mosquito population dynamics.
Our goals are to gather mosquito population data to determine the extent to which urban settings affect mosquito breeding, use the findings to add on to pre-existing models, provide additional insight into one of the key contributors of mosquito population growth, and to create a predictive model to help prevent cases in urban areas in the event of a positive correlation. Through the Globe Data Access Tool and land cover and mosquito habitat entries, we expect to prove a hypothesis of higher urbanization associating with greater proportions of mosquito larvae. This will be done by using the data in graphs and tables to compare the density of mosquitoes in a localized area and prevent uncontrolled variables in our experiment, such as weather and water proximity. We will analyze our data and make a model based on the correlation between urbanization and mosquito population dynamics.
Okay, so just a little bit of background on our hypothesis. We chose to use an urban setting over a rural setting because urban areas tend to be hotter, and this is due to urban heat islands, which are caused by the lack of open space, greenery, and overall light colors in cities. With plants unable to provide transpiration and the darkness of common building materials with a low albedo, urban environments can create increased temperatures compared to their rural counterparts. Going off the increased temperatures in urban settings, mosquitoes tend to like higher temperatures, with them hitting peak performance at 80 degrees Fahrenheit, becoming lethargic at about 60 degrees Fahrenheit, and then completely losing all functionality at any temperature at or below 50 degrees Fahrenheit. Also, urban areas tend to have a lot more people than rural areas, especially in the United States, with urban areas having a lot more opportunity for the mosquitoes to feed.
The association we find varies greatly depending on the scope of the citizen science data we gather.
First, we filtered data by only a handful of states in the same climate zone. We found a correlation coefficient of 0.55, indicating a moderate and positive association between our two variables, and 30.2% of the variation in larvae counts could be explained by urbanization. When we expanded the scope of our data to include several more states in that region and graphed that data, we found a correlation coefficient of only about 0.077, indicating a very weak association, and that about 0.6% of the variation in larvae counts could be explained by urbanization.
Some of our favorite features of the Earth Systems Explorers internship was the opportunity to collaborate with a group of like-minded peers, as well as learn from a diverse group of NASA scientists. One challenge of the internship was definitely creating an entire project from scratch and presenting it virtually.
Personally, I feel like I've learned a lot from the internship, and having the opportunity to work and collaborate with my teammates has given me skills that will last a lifetime.
As an intern in the Earth Systems Explorers group, I was able to analyze citizen science data, learn to use digital tools, and work collaboratively with my team to complete a project, and it's made me more passionate about exploring the intersection of business and computer science.
The Earth Systems Explorers program taught me many valuable skills which I was able to use during my research project and in the future. I had a great experience working with my team, and I improved upon my data collection and analysis skills.
I would like to apply my skill sets and my experience gained from this internship to future job prospects and internship opportunities.
The SEAS internship gave me the opportunity to work with other interns to accomplish a common goal in a set time. It gave me skills that will last a lifetime.
To wrap this up, we would like to give a special thank you to our fantastic mentors for all the help they've given us throughout the research. We also appreciate and admire the work from Cassie, Rusty, and most of all, we hold special thanks to Peter and his consistent positive outlook. Along with these wonderful advisors, we would love to express our gratitude to our peer mentor Aiden for getting the ball rolling and to our other peer mentor James for giving us feedback along the way. We can attribute most of what we've learned to their incredible backgrounds and willingness to help us become better scientists. Thank you all so much.
So thanks to all the teams that presented. We do have several questions. We'd like for you to please turn on your mics, and we want to see those faces. So we have a question for team number 5. Was there anything that surprised you while researching wildfires?
I can take this one. So one thing that definitely surprised us the most was that many of these wildfires had really similar characteristics and occurred under the same seasons. And by being able to identify all these characteristics, it lets us translate this to not just the ones that we studied, but also can apply to most large-scale forest fires around the world.
Another question for team 5. Did you learn a lot about wildfires that you did not know prior to coming to SEAS?
I could go ahead and take this one, but yeah, I think the answer to that's definitely yes. We did a lot of background research. Specifically, we focused on wildfires in California, and that's just like a new topic to, I believe, everyone in our group.
Great. And team number 6, will you continue working on this project after SEAS?
I can take this question. Yes, we do intend on continuing our project. Because of time constraints, we weren't able to do everything we wanted, but we do want to implement more features in the app that can classify all the different features on the Globe app, like different types of trees and shrubs and things like that. And we also want to output percentages of how much of each feature is present in an image, like how we have to do on the actual app. And then our final goal is to build an app that actually is like a companion to Globe Observer, that people can just use and like transport their images over there, and then the suggestions are given, and then they can continue with their observations.
And also for team number 6, how long did it take to develop your model from start to finish?
Oh, I can take that one. So it took us probably in total 1 to 2 days if you count. So our first step was data processing, and that was actually taking all of the images that we had and organizing them in a way that was easy to access with the model. And then we were able to use some libraries, particularly PyTorch and Scorch, which are really good ways of implementing models. And we were able to take a pre-trained model and fine-tune it on our own data. To actually train the model, it took around 1 to 2 hours for training for each model, and we trained 3 individual models, so that took around 6 hours in total, which we did overnight. And then analyzing the results took a few hours and making graphs and things like that. So overall, yeah, a few days.
And another question for Team 6. You mentioned inconsistent labeling. How would you improve on that?
Yeah, for inconsistent labeling, we actually had 2 ideas, and those were either a short training course where participants would see 15 to 30 images to see what they did wrong, other people did wrong, or what to do right. Or we could have a screening process where more experienced users who are better at labeling could proceed and label more images.
Great. And then we have a couple of questions for team number 7. Do you think there are other influences in those states other than urbanization, which would explain your results?
I can take this one. Yeah, I think one of the biggest challenges for us was getting the most amount of data possible, but also doing it in a small enough region where we could control variables like air temperature, surface temperature, climate in general. So yeah, that was one of the challenges with our project. I definitely think there are other things that could impact it, but unfortunately, we weren't able to get to that part of it where we could explore why we weren't seeing the correlation we wanted to. But yeah, definitely.
And a second question for team number 7. Do you think the time of year makes a difference with your research, seeing as one team mentioned they found higher populations in rural areas at a particular time of the year?
I can take this one. So I do think the time of year makes a difference with our research, as in summer, that's usually when mosquitoes come out and breed. So we did get a lot of data from more southern regions in the United States because it tends to be warmer and more humid, to try to keep the data more consistent rather than looking to more northern regions which tend to be drier and colder throughout the other 3 seasons.
Great. Well, you have all done an excellent job with your research, and we really appreciate your time and your efforts. The Earth System Explorers is our largest intern project group. A special thanks goes to the mentors and the peer mentors for their dedication to our interns. Your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. Selena and I thank you for your time and your talent that you've shared with our student interns. I know the SEA's interns appreciate your guidance and advice as they conducted their research. The success of SEA's is determined not only by the commitment and research conducted by the student interns, but also by the mentors and our project assistants. To our NASA subject matter experts and project assistants, your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. Selena and I thank you for your time and your talent that you shared with our student interns. I know the SEA's interns appreciate your guidance and advice as they conduct their research. So thank you for joining us for day 1 of the NASA SEA's Science Symposium. Please join us again tomorrow at 12:30 Central Time as we continue to share the research from NASA's STEM Enhancement in Earth and Space Science high school interns. Thanks for joining.